What if I told you that right now, at this very moment, a bubble of absolute destruction could be racing toward Earth at the speed of light, and we would have no warning, no time to react, no possibility of escape? Not a bubble of fire, not an explosion, something far more fundamental, a bubble of different physics. Inside this bubble, the laws of nature as we know them simply cease to exist. Atoms cannot hold together. Chemistry becomes impossible. The electromagnetic force that binds matter fundamentally changes, and this bubble, once formed, expands forever at light speed, consuming everything in its path, rewriting the very fabric of reality itself. This isn't science fiction. This is vacuum decay, a prediction that emerges from our most successful theories of particle physics. And here's what keeps physicists awake at night. We have no way to prove it won't happen. In fact, measurements from the Large Hadron Collider suggest we may be living in exactly the kind of universe where this catastrophe is not just possible, but inevitable. Think about the ground beneath your feet. It feels solid, permanent, eternal. The atoms in the rock, in the soil, in your own body, they've existed in their current form for billions of years. The electron orbiting the nucleus of every atom in your body does so because of laws of physics that have remained unchanged since the first fraction of a second after the Big Bang. Or have they? What if the stability we perceive, the permanence of physical law, the unchanging nature of fundamental constants is an illusion? What if we're living on borrowed time in a universe that looks stable but is actually perched precariously on the edge of a quantum cliff?
Imagine the universe as a ball resting in a valley between mountains. We assume we're at the bottom, the lowest, most stable point. The ball has settled there. It's not moving. Everything seems fine. But what if we're not at the true bottom? What if we're sitting on a false bottom, a shelf partway down the mountain? Below us, invisible and inaccessible by any classical means, lies the true valley, the real ground state of the universe. Under normal circumstances, the ball can't reach that true valley. There's a barrier, the edge of the shelf. To fall to the true bottom, the ball would need enough energy to climb up and over that edge before falling down, and it doesn't have that energy. But this is where quantum mechanics changes everything. At the quantum level, the ball doesn't need to go over the barrier. It can tunnel through it. There's always a probability, however infinitesimally small, that the ball simply appears on the other side of the barrier, having quantum tunneled through solid rock. And when that happens, when that 1 in 10 to the 100 quantum fluctuation finally occurs somewhere in the vast expanse of space, everything changes. A bubble forms, a tiny sphere, smaller than an atom, where the fundamental ground state of the universe has shifted from false to true, where the Higgs field, an invisible field that permeates all of space and gives particles their mass, has dropped to a lower energy value. Inside this sphere, physics is different. Electrons have the wrong mass, quarks interact with the wrong strength. The fine structure constant, the number that determines how strongly electrons and photons interact, has a different value. But the bubble doesn't stay tiny. The true vacuum has lower energy than the false vacuum, and nature, left to its own devices, always seeks the lowest energy state. That energy difference, the gap between false and true vacuum, becomes kinetic energy, the energy of motion. The bubble wall begins to move, slowly at first perhaps, but within fractions of a second it accelerates to the speed of light and stays there forever.
As the wall expands, it converts everything it touches from false vacuum to true vacuum. The Higgs field drops, particle masses change, fundamental constants shift. Atoms in the bubble's path cannot maintain their structure. The electrons that orbit nuclei either bind too tightly or not at all. Nuclear forces change strength, causing atomic nuclei to either fly apart or collapse. Chemistry, the entire complex dance of electron interactions that makes molecules possible, simply stops working. Planets dissolve, stars flicker out, galaxies crumble, not because they're hit by some external force, but because the internal rules that allow them to exist have been rewritten. And the bubble expands forever. Because it moves at light speed, it can never slow down, never stop. The boundary between existence and non-existence races through the cosmos at 299,792,458 meters per second, consuming everything, leaving behind what? We don't know. We can't know. Whatever exists in the true vacuum is so different from our physics that we cannot predict what forms matter might take there. Perhaps just a thin soup of particles and radiation, perhaps nothing at all, perhaps structures we cannot even imagine, built from physics we cannot comprehend. But here's the truly terrifying part. We would have absolutely no warning. Light travels at light speed. The bubble wall travels at light speed. The information that the bubble exists propagates outward at exactly the same speed as the bubble itself. By the time light from the bubble wall reaches your eyes, the wall has already reached your body. There is no gap, no moment of awareness, no instant of recognition. You wouldn't see it coming. You wouldn't feel anything. One moment you exist, the next moment the physics that allows your existence has been overwritten. Consciousness doesn't fade, it's simply edited out of the cosmic story, as if it never was. Could we escape by running away? No. The bubble expands at exactly light speed. Even if you could accelerate to 99.9999% of light speed, the bubble would still catch you. Even if you could reach exactly light speed, which you can't because you have mass, the bubble would keep pace, never falling behind. There is no escape. There is no defense. There is no warning. This is vacuum decay, and the mathematics that describes it comes from the same quantum field theory that predicted the existence of the Higgs boson before it was discovered, that calculated the magnetic moment of the electron to 12 decimal places, that has passed every experimental test we've thrown at it for 70 years. We're not talking about speculation. We're talking about sober predictions from our most successful theory of fundamental physics. Today, we journey through the evidence that suggests our universe exists in a precarious state called a false vacuum, a metastable configuration that could, at any moment, decay into something completely different. We'll examine the particle physics that predicts this possibility, the measurements from billion-dollar experiments that confirm the necessary parameters, the observations from cosmology that constrain what's possible, and the profound implications for the fate of everything that exists. We'll explore why the universe has survived for 13.8 billion years without decaying. We'll investigate what might trigger the transition from false to true vacuum. We'll discuss what leading physicists believe about the probability and timeline of vacuum decay, and we'll confront the ultimate question: is our universe eternal, or are we living on borrowed time? The answers are disturbing, the implications are profound, the uncertainty is genuine. Prepare yourselves. We begin.
Our story begins not with a distant star or cosmic phenomenon, but with something invisible that permeates every cubic centimeter of space. Something that was discovered accidentally, yet has become central to our understanding of why the universe looks the way it does. July 4th, 2012. Deep beneath the French-Swiss border, in a circular tunnel 27 kilometers in circumference, protons were colliding at nearly the speed of light.
The Large Hadron Collider, the most expensive scientific instrument ever built, costing over $10 billion and requiring the cooperation of thousands of scientists from over 100 countries, had been searching for a single particle, the Higgs boson. At 9 a.m. Geneva time, in a packed auditorium at CERN, physicist Joe Incandela stepped to the podium. Behind him, a graph showed a clear bump, a signal rising above the background noise at an energy of 125 billion electron volts. The data was unmistakable. After analyzing hundreds of trillions of particle collisions, filtering through petabytes of data, the team had found it. "We have observed a new particle," Incandela announced, his voice betraying carefully controlled emotion. "It is consistent with the Higgs boson." The room erupted. Scientists who had dedicated their entire careers to this search stood and applauded. In the front row, 83-year-old Peter Higgs, the physicist who had predicted this particle's existence in 1964, wiped tears from his eyes. This was supposed to be a moment of pure triumph. The standard model of particle physics had predicted the Higgs boson as a necessary consequence of how particles acquire mass. Its discovery confirmed nearly 50 years of theoretical predictions. The champagne flowed. The Nobel Prize followed in 2013, awarded to Peter Higgs and François Englert for their theoretical work predicting the boson. But behind the celebration, a quiet unease began to spread through the theoretical physics community. Not because the Higgs boson existed, that was expected, even required by the theory. The problem was its mass. That specific number, 125.09 GeV, measured with increasing precision as more data accumulated over the following years. This value seemed innocuous, just another experimental measurement. But when theoretical physicists plugged this number into their equations, calculating what it implied for the underlying structure of the universe, they discovered something profoundly disturbing. To understand why, we need to understand what the Higgs field actually is and why it's unlike anything else in our everyday experience. Imagine you're swimming in an ocean. The water is all around you, creating resistance when you move. This resistance is what we perceive as the water's viscosity. It takes effort to push through it. Now imagine this ocean exists everywhere, permeating all of space. Even in what we call a vacuum, even in the emptiest regions between galaxies, this ocean is there. This is the Higgs field. But instead of water, it's a quantum field, a fundamental entity that exists at every point in space. And instead of creating viscosity when you move through it, it creates something more fundamental: mass. Every particle in the universe moves through the Higgs field constantly. Some particles, like electrons, interact strongly with the field. This strong interaction is what we measure as the electron's mass. Other particles, like photons, don't interact with the Higgs field at all, which is why light has no mass and can travel at the speed of light. The Higgs boson itself is a quantum of the Higgs field, a ripple in this cosmic ocean made manifest as a particle when you pump enough energy into a small enough region of space. But here's where it gets strange and where the trouble begins. Quantum fields aren't static, they fluctuate. Even in empty space with no particles present, quantum fields are constantly bubbling with virtual particles that pop into existence and annihilate within fractions of a second. These quantum fluctuations are not hypothetical. They have measurable effects, like the Casimir force between closely spaced metal plates. For the Higgs field, these quantum fluctuations mean the field is constantly jittering around some average value. That average value, the background level of the Higgs field, is what determines particle masses throughout the universe. But what determines what that average value should be? This is where potential energy comes in. Every field has a potential energy curve, a mathematical function that tells you how much energy is associated with different values of the field. The field naturally wants to settle into the configuration with the lowest possible potential energy, like a ball rolling to the bottom of a valley. For the Higgs field, the potential energy curve has a specific shape determined by the field's self-interactions and its interactions with other particles. In the simplest models developed in the 1960s, this potential had a distinctive shape: high energy when the field value is 0, dropping down to a circular trough at some non-zero field value, with a little bump in the middle. The Higgs field settles into that trough, the minimum of the potential energy curve. This is the vacuum state of the universe, the ground state, the configuration with lowest energy. Or so everyone thought. When physicists calculated the actual shape of the Higgs potential using the precisely measured Higgs mass, including all the quantum corrections from virtual particles, they discovered something unexpected. At low energies, the energies we experience in everyday life, even the energies accessible in particle accelerators, the potential looks as expected. There's a minimum, and the Higgs field sits in it, stable and comfortable. But at very high energies, higher than we can directly probe with experiments, the potential changes shape. The quantum corrections, particularly those from the top quark, the heaviest known fundamental particle, become significant. These corrections are negative. They make the potential curve downward. And at energies around 10 to the 11th GeV, far beyond anything achievable in accelerators, but far below the Planck energy where quantum gravity becomes important, the potential develops a second minimum, a deeper valley, a true ground state lower in energy than the one we currently occupy. The realization sent shockwaves through the theoretical community. Our universe isn't sitting at the bottom of the energy landscape. We're sitting on a shelf, a local minimum that looks stable from our perspective, but isn't the true lowest energy state. We're in a false vacuum. In September 2012, just months after the Higgs discovery, physicists Joseph Licken from Fermilab and Alessandro Strumia from the University of Pisa published a paper titled Higgs Boson Mass and New Physics. Their calculations, using the precisely measured Higgs mass, concluded that the standard model vacuum is metastable. The measured values of the Higgs and top quark masses, they wrote, indicate that the standard model potential develops an instability at high energy scales. Metastable. The word sounds benign, almost comfortable. Meta meaning beyond or transcending, stable meaning unchanging. But in physics, metastable means something very specific and very dangerous. A metastable state is a state that appears stable but isn't truly stable. It's stable against small perturbations, but given the right conditions, or simply given enough time, it will eventually transition to the true stable state. Imagine a ball sitting in a shallow bowl on a table. The ball is metastable. Small nudges will cause it to roll around the bowl, but it stays in the bowl. It appears stable. But the ball isn't in the lowest energy state possible. The floor below the table is lower. If the ball could somehow get out of the bowl, it would fall to the floor. The universe is that ball. The false vacuum is that bowl. And quantum mechanics provides a way for the ball to spontaneously tunnel through the bottom of the bowl, appearing on the floor below without ever going over the edge. The implications were staggering. Our universe, ancient, vast, apparently eternal, might be temporary, not on human timescales, not even on cosmic timescales measured in billions of years, but temporary nonetheless, with a finite lifetime before quantum tunneling causes it to decay to the true vacuum state. And when that decay occurs, the consequences would be absolute. The paper's conclusion was sober, but chilling. If the electroweak vacuum is metastable, its lifetime might exceed the present age of the universe by many orders of magnitude, or might be comparable to it. Many orders of magnitude longer than 13.8 billion years means we're probably safe, but might be comparable to it means there's a non-zero chance the universe could decay tomorrow. The discovery of the Higgs boson had solved one mystery, how particles acquire mass, but opened a far deeper and more troubling question. How long does the universe have left?
To understand what false vacuum truly means and why it represents such an existential threat, we need to delve deeper into the quantum mechanics that governs the behavior of fields. Start with the simple analogy again. A ball sitting in a shallow bowl that's positioned on a table. The ball is stable. It's not rolling around. It's in a local minimum, a valley in the energy landscape. But the table itself is elevated. Below the table, there's the floor, the true minimum, the lowest possible energy state. In our universe, the Higgs field is that ball, and it's sitting in that shallow bowl. But calculations suggest there's a much deeper valley that represents a lower energy state, the true vacuum. The only thing keeping the Higgs field from falling to that lower state is a barrier, like the edge of the bowl. Now, under classical physics, the physics of Newton, of everyday experience, the ball would never escape the bowl on its own. Without enough energy to climb up and over the edge, it's trapped forever. The barrier is absolute. But we don't live in a classical universe. We live in a quantum universe, and quantum mechanics rewrites the rules in fundamental ways. In the quantum realm, particles aren't really particles in the classical sense. They're wave functions, probability distributions that describe where the particle might be found if you measure it. And these wave functions don't respect barriers the way classical objects do. Here's the key insight. When a particle encounters a barrier, a region where classical physics says it cannot go because it lacks the energy, its wave function doesn't stop at the barrier's edge. It extends into and through the barrier, decreasing exponentially, but never quite reaching zero. This means there's always a small probability that when you measure the particle's position, you'll find it on the other side of the barrier, even though it never had the energy to classically go over the barrier. This phenomenon is called quantum tunneling, and it's not hypothetical or speculative. It's a well-established effect that's been measured countless times in laboratories. Tunneling is essential to the operation of tunnel diodes used in electronics. It's the mechanism by which radioactive nuclei decay through alpha emission. It's what allows nuclear fusion to occur in the sun's core at temperatures far too low for fusion to happen classically. Quantum tunneling is real, measurable, and absolutely fundamental to how the universe works. Now apply this to the Higgs field. The Higgs field, sitting in its false vacuum state, is separated from the true vacuum by an energy barrier. Classically, the field cannot cross this barrier. It would need to temporarily gain energy to climb up to the barrier's peak before rolling down into the true vacuum on the other side. But quantum mechanically, the field can tunnel through the barrier. At any point in space, at any moment in time, there's a probability that the Higgs field spontaneously appears in the true vacuum state, having tunneled through the barrier without ever going over it. That probability is extraordinarily small, far smaller than the probability that all the air molecules in the room you're in spontaneously move to one corner, leaving you in vacuum. But it's not zero. It's never zero. And in a universe with roughly 10 to the 80 particles extending across 10 to the 26th meters, existing for 10 to the 17 seconds so far, even extraordinarily unlikely events eventually occur. When they do, when somewhere at some random location in space, the Higgs field quantum tunnels from false vacuum to true vacuum, something remarkable happens. A bubble forms.
At that location, the Higgs field has dropped to its true vacuum value. But the field doesn't exist in isolation. The Higgs field at nearby points is still in the false vacuum state. There's now a boundary, a wall separating the true vacuum region from the surrounding false vacuum.
This wall is not made of matter. It's a configuration of the Higgs field itself, a region where the field rapidly transitions from its false vacuum value to its true vacuum value over a very short distance, perhaps 10 to the negative 15 meters or less. But here's where the physics becomes inexorable and terrifying. The true vacuum has lower energy than the false vacuum. That's what true vacuum means. It's the state with absolutely lowest energy. The false vacuum has higher energy. That energy difference, the gap between false and true vacuum energy density, exists throughout all the space occupied by the bubble. In a bubble with radius r, the volume is 4/3 pi r cubed. If the energy density difference between false and true vacuum is delta E, then the total energy released by converting that volume from false to true vacuum is 4/3 pi r cubed times delta E. This energy has to go somewhere, and in relativity, energy and mass are equivalent. Energy has inertia. Energy has momentum. The energy released by vacuum decay goes into the kinetic energy of the bubble wall. The wall begins to move outward, expanding the bubble, converting more false vacuum to true vacuum, releasing more energy, which accelerates the wall further. The equations of motion for the bubble wall can be derived from general relativity. They show something remarkable. Once the bubble forms and begins expanding, it very rapidly accelerates to the speed of light. Not close to the speed of light, not 99% of the speed of light, exactly the speed of light. The bubble wall becomes a relativistic shock front, a discontinuity in space-time moving at the maximum possible speed. And because it's moving at light speed, it can never slow down. There's no friction, no resistance. The wall just keeps going, expanding the bubble forever. This isn't speculation. This is what Einstein's equations demand. This is what happens when you have a first-order phase transition in a relativistic quantum field theory. Sidney Coleman, one of the greatest quantum field theorists of the 20th century, worked out the mathematics in the 1970s, decades before the Higgs boson was discovered. His paper, The Fate of the False Vacuum, published in Physical Review D in 1977, remains the foundation for all modern calculations of vacuum decay. Coleman showed that once a bubble forms, its evolution is determined entirely by the energy difference between false and true vacuum. For any significant energy difference, the bubble wall reaches light speed effectively instantaneously. And as the wall expands, it converts everything it touches. Inside the bubble, the Higgs field has a different value. This means particles have different masses. The electron's mass might be different, perhaps heavier, perhaps lighter, perhaps zero. The up quark and down quark, the particles that make up protons and neutrons, would have different masses, changing the binding energy of atomic nuclei. The electromagnetic force, which binds electrons to nuclei, has its strength partially determined by the Higgs field value. In the true vacuum, with a different Higgs field value, the electromagnetic force would be different. Chemistry depends exquisitely on the precise strength of electromagnetic interactions and the precise masses of electrons. Change these parameters even slightly, and familiar molecules cannot form. Change them significantly, and atoms cannot exist in any recognizable form. The strong nuclear force, the force that binds quarks together into protons and neutrons and binds protons and neutrons together into atomic nuclei, also depends on quark masses. In the true vacuum, the strong force might be too weak to bind nuclei together, or too strong, causing all matter to collapse into strange quark nuggets. We cannot predict exactly what would exist in the true vacuum because we don't know precisely how the forces change, but we know they would change. We know the familiar physics we depend on would cease to function.
Stars couldn't burn through nuclear fusion. Planets couldn't form from gravitationally bound matter. Complex molecules couldn't exist. Life would be impossible. And the transition happens at light speed, which means there's no warning, no time to react, no possibility of escape. Think about what moving at light speed means. Light from the sun takes 8 minutes to reach Earth. That's 8 minutes of warning if something happened to the sun. But a vacuum decay bubble wall moving at light speed provides 0 warning. The light informing you of the bubble's existence travels at the same speed as the bubble itself. Imagine standing on train tracks with a train approaching at light speed. You can't see the train coming. The light from the train's headlights and the train itself arrive simultaneously. One moment you're standing safely on the tracks. The next moment, no gap, no interval, no transition, you're hit. That's vacuum decay. Instantaneous, unavoidable, final. In 1980, physicists Michael Turner and Frank Wilczek, who would later win the Nobel Prize for his work on quantum chromodynamics, published a paper analyzing the vacuum decay bubble's structure in detail. They calculated the energy density in the bubble wall, the thin shell where the Higgs field transitions from false to true vacuum. The energy density is enormous, comparable to the energy density in the early universe fractions of a second after the Big Bang. The wall is literally a shell of concentrated energy racing outward at light speed. If you could somehow observe the bubble from outside, which you can't because you'd be inside it before you could see it, it would appear as an expanding sphere of light, bright beyond imagination, converting the universe from one state to another. But from inside, you'd experience nothing. The physics that allows neurons to fire, that allows consciousness to exist, would simply stop functioning. There would be no moment of awareness, no instant of terror. Existence would simply stop. The mathematics is clear. The physics is well established. The implications are absolute. Once vacuum decay begins, it cannot be stopped. The bubble expands forever at light speed, consuming everything. There is no defense, there is no escape. There is only the inexorable expansion of the true vacuum, replacing the metastable false vacuum we call home.
When these calculations first emerged in the wake of the Higgs discovery, the obvious question arose: if vacuum decay is possible, why hasn't it happened already? The universe is 13.8 billion years old, 13,800,000,000 years, or about 4.3 times 10 to the 17 seconds. That's a long time by human standards. But is it a long time by the standards of quantum tunneling? Is it surprising that vacuum decay hasn't occurred yet? To answer this, physicists needed to calculate the decay rate, the probability per unit time per unit volume that a vacuum decay bubble will spontaneously form through quantum tunneling. This calculation is extraordinarily difficult. It involves evaluating what physicists call the bounce solution, a particular configuration of the Higgs field in both space and imaginary time that represents the quantum tunneling process. The mathematics involves path integrals, instantons, and sophisticated field theory techniques developed over decades. But the basic result can be understood without diving into the technical details. The probability of quantum tunneling through a barrier depends exponentially on what's called the action of the bounce solution. The action is a quantity that encodes both the height of the barrier and its thickness. Higher barriers mean smaller tunneling probabilities. Thicker barriers mean smaller tunneling probabilities. For vacuum decay, the barrier is the potential energy difference the Higgs field would need to overcome to classically transition from false vacuum to true vacuum. This barrier is high, very high. The Higgs field would need to temporarily acquire enormous energy, far beyond anything we can produce in particle accelerators. When physicists calculate the tunneling probability using the measured Higgs mass and top quark mass, they get decay rates with extraordinary numbers attached. The half-life of the false vacuum, the time it would take for there to be a 50% probability that vacuum decay occurs somewhere in a volume the size of the observable universe, is estimated to be somewhere between 10 to the 100 and 10 to the 600 years, depending on the precise values of parameters we haven't measured perfectly, and on unknown physics at very high energies. Let's put these numbers in perspective. 10 to the 100 years is a Google years. That's a 1 followed by 100 zeros. The current age of the universe is about 1.4 times 10 to the 10 years. A Google years is 90 orders of magnitude longer than the current age of the universe. To visualize this, if the current age of the universe were represented by a single second, a Google years would be 10 to the 90 seconds, which is far, far longer than the universe's current age measured in any unit. And that's just the low end of the estimate. The high end, 10 to the 600 years, is so large that it defies comprehension. That's a 1 followed by 600 zeros. There aren't enough particles in the observable universe to write out this number if you used 1 particle per digit. So we're safe, right? The vacuum might be metastable, but it's metastable on timescales so long that calling them astronomical is a ridiculous understatement. But here's where it gets complicated. These calculations assume several things. They assume the universe continues in its current state, stable, expanding, but relatively calm. They assume no high-energy events occur that could potentially trigger vacuum decay. They assume the standard model of particle physics continues to hold at all energies up to where the true vacuum lies. Each of these assumptions might be wrong. First, the uncertainty in these lifetime calculations is huge. The tunneling rate depends exponentially on the action, which in turn depends on parameters like the exact mass of the Higgs boson, the exact mass of the top quark, the exact strength of the Higgs self-coupling, and other quantities we've measured but not with perfect precision. Current measurements of the Higgs mass have an uncertainty of about 0.2%. The top quark mass has an uncertainty of about 0.5%. These sound like small uncertainties, and they are, representing incredible experimental achievement. But when these uncertainties are fed into the exponential formula for tunneling probability, they translate to factors of 10 to the 100 or more in the vacuum lifetime. A small change in the top quark mass, from 172.9 GeV to 173.1 GeV, well within current measurement uncertainty, could shift the vacuum lifetime from 10 to the 500 years to 10 to the 100 years, or vice versa. We're not even sure if the vacuum is truly metastable. With current measurement precision, it's possible the vacuum is actually absolutely stable, with no second minimum at all. Or it could be much more metastable than the median estimates suggest. In 2014, a team led by Dario Butazzo at CERN published a comprehensive analysis incorporating all measurement uncertainties. Their paper, Investigating the Near Criticality of the Higgs Boson, found that with 95% confidence, the vacuum is either metastable with an extremely long lifetime or absolutely stable, or right on the edge between the two. The edge, that word keeps coming up. The standard model appears to be fine-tuned to place us right at the boundary between stability and metastability. Is this a coincidence, a clue, or something we don't yet understand? Second, these calculations assume no external triggers. They calculate the probability of spontaneous vacuum decay through pure quantum fluctuation. But what if something could trigger the decay? What if high-energy events could catalyze the transition, making it more likely? This is where cosmic rays become relevant.
Cosmic rays are particles, mostly protons, accelerated to enormous energies by astrophysical processes. Supernova shock waves, the magnetospheres of pulsars, the jets from active galactic nuclei powered by supermassive black holes, all of these can accelerate particles to energies far exceeding anything achievable in human-built accelerators. The Large Hadron Collider collides protons at energies of 14 trillion electron volts, 14 TeV. This is extraordinary by human standards. It requires superconducting magnets cooled to 1.9 Kelvin, just above absolute zero, consuming power equivalent to a small city. But nature routinely produces cosmic rays with energies 1,000,000 times higher. The highest energy cosmic ray ever detected was observed on October 15, 1991, by the Fly's Eye Cosmic Ray Detector in Utah. The particle, likely a proton, carried an energy of about 3 × 10 to the 20th electron volts, or 300 eeV, exa-electron volts. To put this in perspective, this single subatomic particle carried kinetic energy equivalent to a baseball traveling at 100 kilometers per hour. That's macroscopic energy concentrated in a single proton. When this particle struck Earth's atmosphere, it created a cascade of secondary particles that lit up the detector array. The energy was so high that physicists initially thought it was an error. Nothing in known astrophysics should be able to accelerate particles to such energies, yet there it was. This particle was dubbed the "Oh my God" particle, and it remains the highest energy cosmic ray ever detected. But it's not unique. Ultra-high energy cosmic rays, particles with energies above 10 to the 19 eV, are rare, but not extraordinarily so. Detectors observe roughly 1 per square kilometer per century at the highest energies. And the Earth has a large area. The Earth's cross-section facing space is about 125 million square kilometers. Over the Earth's 4.5 billion year history, ultra-high energy cosmic rays have bombarded our planet countless times. Scale this up to the universe. There are approximately 10 to the 24 stars in the observable universe, most with planets. Cosmic rays have been striking surfaces throughout the cosmos for 13.8 billion years. The total number of ultra-high energy cosmic ray collisions throughout cosmic history is roughly 10 to the 60th or more, and none of them triggered vacuum decay. This is a powerful constraint. If vacuum decay were easily triggered by high-energy collisions, it would have happened by now. The fact that we exist, that the universe still exists in its current form, tells us something important. Either the vacuum is very stable, or the threshold energy for triggering decay is very high, higher than even the most energetic cosmic rays. In 2015, physicist Vincenzo Broncina and colleagues published calculations analyzing what cosmic ray observations tell us about vacuum stability. They showed that if the vacuum could be triggered to decay by energies achievable by cosmic rays, it would have decayed long ago. Therefore, either the vacuum is absolutely stable, no true vacuum exists, or the vacuum is metastable, but the barrier is so high that even cosmic ray energies can't trigger decay. Or the triggering mechanism requires not just high energy, but specific conditions that cosmic ray collisions don't provide. This is sometimes called the cosmic ray argument, and it provides strong evidence that we're not in immediate danger from vacuum decay, at least not from the kind of random high-energy events that occur naturally in the universe. But, and this is crucial, the cosmic ray argument doesn't prove safety forever. It only proves that random, naturally occurring high-energy collisions haven't triggered decay in 13.8 billion years. The calculation that vacuum decay could happen spontaneously through quantum tunneling without any trigger, just through random quantum fluctuation, remains valid, and those timescales are 10 to the 100 years or more, far longer than the 13.8 billion years the universe has existed. So, the cosmic ray argument and the spontaneous decay calculations are consistent. The vacuum hasn't decayed in 13.8 billion years because the probability of decay over that time is extraordinarily small. But given enough time, googles of years, decay becomes probable, unless something else happens first. There's a third consideration. The universe is not static, it's evolving. and that evolution might change the vacuum decay probability. Right now, the universe is expanding, and that expansion is accelerating. This acceleration is driven by dark energy, a form of energy that fills all of space uniformly and has negative pressure. The simplest explanation for dark energy is that it's the energy of the vacuum itself. But if the vacuum can decay, what happens to dark energy? In the true vacuum, the vacuum energy density would be different, likely much more negative. This would change the expansion rate of the universe, potentially causing it to collapse in a big crunch rather than expand forever. More speculatively, some physicists have suggested that the accelerating expansion of the universe might itself affect vacuum stability. As space expands, quantum fluctuations get stretched to larger scales. Could this stretching somehow trigger vacuum decay or prevent it? These questions remain open. The interaction between cosmological expansion and vacuum decay is an active area of research, with papers published regularly exploring different scenarios. What we know for certain is this: the universe has existed for 13.8 billion years without vacuum decay occurring. This places constraints on how unstable the vacuum can be, but it doesn't guarantee the vacuum will never decay. Probability is not protection. An event with probability 10 to the minus 100 per year is extraordinarily unlikely, but it's not impossible. And when that rare event means the end of everything, even tiny probabilities demand attention. The physicist Max Tegmark has pointed out a troubling implication of vacuum metastability. If the vacuum is metastable and will eventually decay, then in some sense we're living in a special time, the period before decay occurs. Most of the universe's history, stretching into the far future, will be after decay, when physics is different and life is impossible. Why do we find ourselves in this special period? The anthropic answer is inevitable, because only in the period before decay can observers exist. We can't observe the universe after decay, because there's no we to observe the universe. But this raises the question, how long will this special period last? Are we early in the universe's metastable phase, with googles of years ahead? Or are we, by cosmic coincidence, living near the end? We can't know. The timing of a quantum tunneling event is fundamentally random. It could happen in the next second, or it could happen 10 to the 1,000 years from now. Quantum mechanics gives us probabilities, not certainties. What we can say is this: based on current measurements and calculations, the probability that vacuum decay will occur in the next billion years, or trillion years, or even 10 to the 50 years is vanishingly small, so small that it's not worth worrying about on any practical timescale. But on timescales of 10 to the 100 years or more, timescales that dwarf even the heat death of the universe, vacuum decay becomes not just possible, but probable. The universe might be eternal, or it might have an expiration date written in quantum mechanics, so far in the future that it's beyond human comprehension, but finite nonetheless.
But the truly disturbing realization emerged when physicists started thinking carefully about what could trigger vacuum decay, what could catalyze the transition from false vacuum to true vacuum without waiting for spontaneous quantum tunneling over googles of years. Remember, vacuum decay happens through quantum tunneling, a probabilistic process where the Higgs field spontaneously appears in the true vacuum state despite the energy barrier. But quantum tunneling rates are not fixed constants. They can be dramatically increased by certain conditions. One of those conditions is energy density. The quantum tunneling probability depends on the action, a quantity that measures how difficult the tunneling process is. Higher barriers mean larger action, which means exponentially suppressed tunneling rates. But if you add energy to the system, you effectively reduce the height of the barrier the field must tunnel through. Think of it this way. If you're trying to tunnel through a mountain, it's easier if you start halfway up the mountain rather than at its base. the barrier is smaller, so the tunneling probability is higher. For vacuum decay, adding energy to the Higgs field, creating high-energy configurations of the field, makes tunneling to the true vacuum more likely. And there's a critical energy scale where the barrier becomes small enough that vacuum decay becomes probable rather than vanishingly unlikely. What kind of energies are we talking about? The precise threshold depends on the details of the Higgs potential, which we don't know perfectly at very high energies. But calculations suggest that energies approaching the Planck scale, about 10 to the 19 GeV or 10 to the 28 electron volts, could potentially reduce the barrier enough to make vacuum decay likely. These are energies that haven't existed in our universe since the very first fractions of a second after the Big Bang, during the period called the Planck epoch, when quantum gravity effects dominated. We're nowhere close to creating such energies artificially. The Large Hadron Collider reaches energies of about 14 TeV, 14 trillion electron volts. That's impressive, but it's still 16 orders of magnitude below the Planck scale. It's like comparing the energy in a AAA battery to the total energy output of the Sun. No particle accelerator we could conceivably build would reach Planck energies. The required accelerator would be larger than the solar system. The power consumption would exceed the total energy output of the Sun. It's not just impractical, it's physically impossible with any technology we can imagine. So we're safe from triggering vacuum decay in our laboratories at least. But nature has no such limitations. Cosmic rays, particles accelerated by extreme astrophysical processes, regularly reach energies far exceeding anything the LHC can produce. Supernova explosions, the jets from active galactic nuclei, the magnetospheres around rapidly spinning neutron stars called pulsars. These natural particle accelerators operate at energy scales that make human technology look primitive. The oh my God particle I mentioned earlier, the cosmic ray detected in 1991 with energy around 3 × 10 to the 20th eV, carried energy about 20 million times higher than the LHC can achieve. Still far below the Planck scale, but getting closer to the range where vacuum stability becomes a question. And these ultra-high-energy cosmic rays have been bombarding Earth and every other planet, moon, and asteroid in the universe for billions of years. If they were going to trigger vacuum decay, wouldn't they have done so already? This is the cosmic ray argument I discussed earlier, and it provides strong evidence that vacuum decay isn't easily triggered. But it's not absolute proof of safety. Here's why. First, even the highest energy cosmic rays are still far below the Planck scale. They might be insufficient to trigger vacuum decay even if energies near the Planck scale could. Second, cosmic ray collisions are localized events. A high-energy proton strikes an atmospheric nucleus, creates a shower of particles, and the energy dissipates. This might not create the extended, coherent excitation of the Higgs field necessary for vacuum decay. Triggering vacuum decay likely requires not just high energy density, but high energy density in a specific field configuration. The Higgs field itself must be excited to high values across some region of space. Random particle collisions might not achieve this, but there are other astrophysical phenomena that might. Black holes. Black holes are regions of spacetime where gravity is so strong that even light can escape. Near a black hole's event horizon, the curvature of spacetime becomes extreme, and in quantum field theory, spacetime curvature can affect vacuum stability. In 1974, Stephen Hawking discovered that black holes aren't entirely black. Quantum effects near the event horizon cause black holes to radiate particles, a phenomenon called Hawking radiation. This radiation has a temperature inversely proportional to the black hole's mass. For large black holes, stellar mass or larger, this temperature is tiny, far below the cosmic microwave background radiation that fills all space. A black hole with the mass of the Sun has a Hawking temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. But as a black hole radiates, it loses mass, and as it loses mass, its temperature increases. The process accelerates. Higher temperature means faster radiation, which means faster mass loss, which means even higher temperature. In the final moments of a black hole's evaporation, when its mass has decreased to microscopic levels, its temperature soars to extraordinary values. When a black hole reaches what's called the Planck mass, about 22 micrograms, roughly the mass of a flea egg, its temperature exceeds 10 to the 32 Kelvin. At this temperature, the Hawking radiation carries energies approaching the Planck scale. These are exactly the energies where vacuum stability becomes questionable. In 2013, physicists Piero Borda, Ruth Gregory, and Ian Moss published a remarkable paper in Physical Review Letters. They calculated the probability that small black holes could seed vacuum decay bubbles. Their analysis showed that the intense curvature of spacetime near a small black hole's event horizon, combined with the extreme energies of Hawking radiation, creates conditions where quantum tunneling to the true vacuum becomes enhanced. The black hole acts as a catalyst, lowering the effective barrier for vacuum decay. For black holes below a certain critical mass, about 10 to the 5th kilograms, about the mass of a small mountain, the probability of catalyzing vacuum decay becomes non-negligible. Do such black holes exist?
We've never detected one directly. All known black holes are stellar mass or larger, at least a few times the mass of the Sun. These massive black holes will take 10 to the 67 years or more to evaporate through Hawking radiation, far longer than the current age of the universe. But primordial black holes, formed in the first second after the Big Bang from density fluctuations, could span a wide range of masses, from microscopic to stellar scale. If primordial black holes exist in the dangerous mass range around 10 to the 5 kilograms, they could be ticking time bombs. These black holes would be evaporating right now, approaching the Planck mass, entering the temperature regime where they might trigger vacuum decay. We've searched for primordial black holes through various methods, looking for their Hawking radiation, watching for gravitational lensing effects, analyzing how they would affect the cosmic microwave background. So far, we've found no definitive evidence they exist in significant numbers. But absence of evidence isn't evidence of absence. Primordial black holes could be rare and difficult to detect. There might be one in our galaxy or in a nearby galaxy, even now, approaching the critical mass where it could catalyze vacuum decay. If that black hole exists, and if it catalyzes vacuum decay, a bubble would form at its location. The bubble would expand at light speed, and we would have no warning until the bubble wall hit us. Even more troubling, stellar mass black holes will eventually evaporate. It will take an incomprehensibly long time, 10 to the 67 years for a solar mass black hole. But if the universe lasts that long, every black hole will eventually shrink to the dangerous mass range. This suggests a disturbing scenario for the far future. Long after the stars have died, long after galaxies have dissolved, long after even protons may have decayed, if they do, the universe could be filled with evaporating black holes. And as each one reaches the Planck mass, it could become a potential trigger for vacuum decay. The far future might be more dangerous than the present. But black holes aren't the only potential trigger. Colliding neutron stars produce energy densities and temperatures approaching those of the early universe. The LIGO Gravitational Wave Observatory detected its first neutron star collision in 2017, designated GW 170817. The gravitational waves from the collision indicated that the neutron stars merged, creating conditions of extreme density and temperature. Could such events trigger vacuum decay? Probably not. The energies involved, while enormous, are still far below the Planck scale, but we can't rule it out completely. Phase transitions in the early universe provide another possible trigger.
In the first fractions of a second after the Big Bang, the universe underwent several phase transitions as it cooled. The electroweak phase transition, when the Higgs field acquired its current value, occurred when the universe was about a piposecond old and had a temperature of about 10 to the 15 Kelvin. During this phase transition, the Higgs field was wildly fluctuating, exploring different values, potentially coming close to configurations where vacuum decay could occur. The fact that the universe survived this period without decaying provides another constraint on vacuum stability. It suggests the barrier to vacuum decay is high enough to survive even the extreme conditions of the early universe. Or perhaps vacuum decay did occur during the early universe, but cosmic inflation, the exponential expansion of space in the first fraction of a second, swept the bubbles away faster than they could grow, preventing them from consuming the universe. Some cosmologists have even suggested that cosmic inflation itself might have been triggered by vacuum decay, a transition from a higher energy false vacuum to our current lower energy but still false vacuum. In this view, the universe has undergone vacuum decay before, and our current vacuum is simply the latest in a series of states. If this is correct, vacuum decay isn't a catastrophe to be feared. It's a process the universe has survived before and might survive again. Each vacuum decay creates a new cosmic bubble universe with different physics, expanding the cosmic landscape of possible physical laws. But there's a crucial difference between vacuum decay during inflation and vacuum decay now. During inflation, space was expanding exponentially fast, faster than light. Vacuum decay bubbles would form, but inflation would sweep them apart before they could coalesce. Now, inflation has ended. Space is still expanding, but much slower. A vacuum decay bubble forming now would expand at light speed into a relatively calm, slowly expanding universe. Nothing would stop it. Nothing would sweep it away. It would just grow, consuming everything forever. Recent theoretical work has explored another potential trigger: quantum computers. Quantum computers operate by manipulating quantum states, superpositions and entanglements of particles in carefully controlled configurations. As quantum computers become more powerful, they might be capable of creating exotic quantum states that we've never observed before. Could a sufficiently powerful quantum computer create a quantum state that triggers vacuum decay? This is highly speculative, and most physicists think it's extremely unlikely. The energy densities in quantum computers are far too low to affect the Higgs field significantly. But the possibility has been raised in theoretical papers, and it illustrates how vacuum decay, once you start thinking about it, creates worry about all kinds of potential triggers. The fundamental issue is this: we don't know where the threshold lies. We don't know what energy density, what field configuration, what specific conditions are required to make vacuum decay likely rather than impossibly rare. We know cosmic rays haven't triggered it in 13.8 billion years. We know the early universe didn't trigger it. These observations constrain the possibilities, but they don't eliminate all risk. Vacuum decay remains a sword of Damocles hanging over the universe, held by a quantum thread that could snap at any moment, or might hold for googles of years. We simply don't know which.
The evidence for vacuum metastability begins with a single number, measured with extraordinary precision through years of painstaking experimental work: 125.09 GeV. This is the mass of the Higgs boson. To measure it, physicists at CERN analyzed millions upon millions of proton collisions from the Large Hadron Collider. Most collisions produced ordinary particles, quarks, gluons, photons. But very rarely, about once every few billion collisions, the energy concentrated enough to create a Higgs boson. The Higgs boson is unstable. It exists for only about 10 to the minus 22 seconds before decaying into other particles.
We never see the Higgs directly. We see its decay products, 2 photons, or 2 Z bosons, or 2 bottom quarks. By carefully measuring the energies and momenta of these decay products and doing complex statistical analysis to separate signal from background, physicists can reconstruct the mass of the original Higgs boson. By 2015, after analyzing the full dataset from the LHC's first run, the mass was pinned down, 125.09 GeV, an uncertainty of less than 0.2%, extraordinary precision for a particle that exists for less than a septillionth of a second. Why does this number matter so much? The mass of the Higgs boson is not an independent, arbitrary parameter. It's related to the strength of the Higgs field's self-interaction, how strongly the field couples to itself. This self-coupling appears in the Higgs potential function and determines the shape of that function at both low and high field values. At low field values, the values relevant to everyday life and current particle accelerators, the Higgs potential has a minimum where the Higgs field sits comfortably. The Higgs mass tells us about the curvature of the potential near this minimum. But what about high field values, corresponding to high energies far beyond what we can directly probe? This is where quantum corrections become crucial. In quantum field theory, what we measure in experiments isn't just the classical behavior of fields. We also measure the effects of virtual particles, particles that pop in and out of existence due to quantum uncertainty, existing too briefly to be directly observed, but nonetheless affecting physical processes. Every particle that couples to the Higgs field contributes quantum corrections to the Higgs potential. These corrections modify the shape of the potential at high energies. Most particles contribute small corrections because they're light and couple weakly to the Higgs field. The electron, for example, has a mass of only 0.000511 GeV and couples relatively weakly to the Higgs field. Its contribution to quantum corrections is tiny. But the top quark is different. The top quark has a mass of 172.76 GeV, about 173 times heavier than a proton, and about 340,000 times heavier than an electron. It's the heaviest elementary particle known. And it couples very strongly to the Higgs field. In fact, the top quark gets essentially all of its enormous mass from the Higgs mechanism. Because of this strong coupling and large mass, the top quark contributes significantly to quantum corrections to the Higgs potential. And crucially, the top quark's contribution is negative. It makes the potential curve downward at high energies. At first, this doesn't cause problems. At moderate field values, the positive contributions from Higgs self-interactions dominate, keeping the potential curved upward and maintaining the minimum where the Higgs field sits. But at very high field values, corresponding to high energies around 10 to the 11 GeV, the negative contribution from top quark loops becomes large enough to overcome the positive contributions. The potential starts curving downward. Keep increasing the field value, and eventually the potential curves down so much that it creates a second minimum, deeper than our current minimum. This second minimum is the true vacuum. The precise energy where this happens depends critically on the exact masses of the Higgs boson and the top quark. Change the Higgs mass by a few percent, and the true vacuum minimum might appear at a different energy, or might not appear at all. Change the top quark mass by a few percent, and the same thing happens. With the measured values of 125 GeV for the Higgs and 173 GeV for the top, the calculations show that a second minimum appears. We live in a false vacuum. In 2012, Giuseppe De Grassi at the University of Rome, along with collaborators Stefano De Vita, Joan Elias Miró, José Espinosa, Gian Giudice, Gino Isidori, and Alessandro Strumia, performed comprehensive calculations incorporating the newly measured Higgs mass. Their paper, Higgs Mass and Vacuum Stability, published in the Journal of High Energy Physics, concluded that with the measured values, the standard model vacuum is metastable. They calculated the energy scale where instability sets in, about 10 to the 11th GeV, or 100 billion GeV. This is far beyond the reach of any current or planned particle accelerator. The LHC reaches 14,000 GeV, about 7 million times too low to directly probe the regime where the potential becomes unstable. But we can calculate what happens there using the standard model equations, extrapolating from the physics we've measured at low energies. The calculation involves what physicists call the renormalization group equations, mathematical equations that describe how coupling constants and masses change with energy scale. These equations are well tested. They correctly predict how the strong nuclear force gets weaker at high energies, a phenomenon called asymptotic freedom, for which the Nobel Prize was awarded in 2004. They correctly predict how the electromagnetic and weak nuclear forces unify at high energies.
Using these same equations to calculate the evolution of the Higgs potential with energy is not speculation. It's applying well-established theoretical techniques. And what these calculations show is deeply troubling. At high energies, the standard model develops a second vacuum state with lower energy than our own. But here's what makes this finding even more disturbing. It's not just that a second minimum exists, it's how close we are to the boundary between stability and metastability. If the Higgs mass were just 5% larger, around 131 GeV instead of 125 GeV, the quantum corrections would be different, and the potential would remain stable at all energies. No second minimum would form. The universe would be absolutely stable, eternal, with no possibility of vacuum decay. If the top quark were just 3% lighter, around 167 GeV instead of 173 GeV, the same thing would happen. The negative quantum corrections would be smaller, and the potential would stay stable. Conversely, if the Higgs were a few percent lighter, or the top quark a few percent heavier, the metastability would be more severe. The barrier between false and true vacuum would be lower. The vacuum lifetime would be shorter, perhaps much shorter. The observed values place us right at the edge, not deep in the metastable region, not safely in the stable region, but right at the boundary. The standard model parameters appear fine-tuned to give us a vacuum that's barely metastable, with a lifetime long enough to survive for cosmological timescales, but not infinite. Is this a coincidence? Some physicists think so. The Higgs mass and top quark mass are what they are. We measure them, we don't choose them. If the measurements place us near a boundary, that's just how nature happens to be. Others see a deeper meaning. The proximity to the stability boundary might be a clue about new physics we haven't discovered yet. Perhaps there are additional particles, not yet detected, that modify the quantum corrections in ways that bring us exactly to this critical point. Perhaps the apparent fine-tuning is telling us something profound about how the universe works. In 2014, physicist Dario Butatso at CERN led a team that performed the most comprehensive analysis yet of vacuum stability, incorporating all measurement uncertainties. Their paper, investigating the near criticality of the Higgs boson, analyzed how uncertainty in the measured parameters translates to uncertainty in vacuum stability. Their conclusion: with 95% confidence, the standard model vacuum is either metastable with an extremely long lifetime, or right at the critical boundary between stability and metastability, or possibly even absolutely stable if the true parameter values lie at the edges of current measurement uncertainty. We cannot say with certainty which we're in. The measurements aren't precise enough yet. We're living with fundamental uncertainty about the ultimate fate of the universe. The implications are staggering. The very theory that has been tested to extraordinary precision over half a century, that predicted the existence of the W and Z bosons before they were found, that predicted the gluon, that predicted the charm and top quarks, that has passed every experimental test ever thrown at it. This same theory, when pushed to its logical conclusions using the measured masses of particles, predicts our universe is not eternal. Not unstable on human timescales, not even unstable on stellar or galactic timescales, but unstable on timescales of googles of years, timescales that dwarf the current age of the universe, but nonetheless finite. The Standard Model, our greatest achievement in fundamental physics, contains the seeds of cosmic destruction embedded in its equations, and those seeds were planted by something as seemingly innocuous as the mass of the Higgs boson having the value 125.09 rather than 120 or 130. A few percent difference in a single measured parameter, and the fate of the universe changes from eternal to temporary. That's how delicate our existence is. That's how finely balanced the cosmos sits on the edge of oblivion.
But here's where the evidence becomes both reassuring and deeply strange. If the universe is metastable and high energies can trigger vacuum decay, why hasn't it happened already? Every second, right now, as you read this, millions of high-energy particles from space are colliding with Earth's atmosphere. These cosmic rays, mostly protons with some heavier nuclei, have been accelerated to extraordinary speeds by some of the most violent processes in the universe. The average cosmic ray is relatively modest in energy, perhaps a few billion electron volts. These particles create faint blue flashes of Cherenkov radiation as they slam into atmospheric molecules, ionize the upper atmosphere, and contribute to the natural background radiation we're all exposed to constantly. But the high-energy tail of the cosmic ray distribution extends to truly extraordinary energies. In 1962, a cosmic ray struck the Earth's atmosphere above Volcano Ranch, New Mexico, with an energy of 10 to the 20 electron volts. Physicists at the time thought it was an error. Nothing should be able to accelerate particles to such energies, but the detection was real. Since then, we've detected dozens of particles with similar or even higher energies. The current record holder, the Oh My God particle, detected in 1991, carried approximately 3 times 10 to the 20 electron volts, equivalent to about 50 joules of kinetic energy. To put that in perspective, that's roughly the kinetic energy of a baseball thrown at 100 kilometers per hour, except this energy was concentrated in a single proton, a particle about 10 to the minus 15 meters across. The energy density was almost incomprehensible. When this particle struck the upper atmosphere, it initiated a cascade of secondary particles, a cosmic ray shower that spread out over several square kilometers. Detectors on the ground registered the shower as thousands of particles arriving simultaneously, all originating from that single primary cosmic ray. What could accelerate particles to such energies? We're not entirely sure. The most energetic cosmic rays have energies 100 million times higher than the Large Hadron Collider can achieve. Even supernova shock waves, one of the most powerful acceleration mechanisms we know, seem insufficient to explain the highest energy cosmic rays. One possibility is that they're accelerated in the jets from active galactic nuclei, the regions immediately surrounding supermassive black holes at the centers of galaxies, where matter falling toward the black hole creates powerful magnetic fields and particle jets traveling at nearly the speed of light. Another possibility involves the magnetospheres of rapidly spinning neutron stars. These magnetars, as they're called, have magnetic fields trillions of times stronger than anything we can create on Earth, strong enough to warp atomic orbitals and potentially strong enough to accelerate particles to extreme energies. A third, more speculative possibility is that the highest energy cosmic rays are created by the decay of exotic super-heavy particles left over from the Big Bang, or by topological defects in space-time, like cosmic strings. We don't know for certain, but we know the particles exist, we know they strike Earth regularly, and we know they've been doing so for billions of years. How regularly? Ultra-high energy cosmic rays, those above 10 to the 19 eV, strike Earth at a rate of about 1 per square kilometer per century. That sounds rare, and on human scales it is, but Earth's cross-sectional area is about 127 million square kilometers. Over Earth's 4.5 billion year history, ultra-high energy cosmic rays have struck our planet roughly 10 to the 15 times. 10 quadrillion collisions, each with energies far exceeding anything the LHC can produce. Now scale up to the entire universe. There are approximately 10 to the 24 stars in the observable universe. Most have planets, moons, asteroids, surfaces that cosmic rays can strike. And cosmic rays have been bombarding these surfaces not just for 4.5 billion years, but nearly the entire 13.8 billion year age of the universe. The total number of ultra-high energy cosmic ray collisions throughout cosmic history is staggering, roughly 10 to the 60 or more. That's a billion trillion 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 collisions, each with energies that would vaporize any human-built instrument designed to measure them. And yet, in all those collisions, across all that time, none triggered vacuum decay. This is powerful evidence. If vacuum decay could be easily triggered by high-energy particle collisions, we wouldn't be here to wonder about it. The universe would have decayed long ago. This observation, called the cosmic ray argument, places stringent constraints on how unstable the vacuum can be. In 2015, physicist Vincenzo Brancina at the University of Catania, along with Emanuele Messina and Mark Schur, published a detailed analysis of what cosmic ray observations tell us about vacuum stability. They calculated the probability that cosmic ray collisions throughout cosmic history would have triggered vacuum decay if the barrier were below certain heights. Their results showed that cosmic ray observations rule out vacuum configurations where the barrier is low enough that energies achievable by cosmic rays could trigger decay. The barrier must be high enough, the false vacuum must be stable enough that even 10 to the 60 ultra-high energy collisions weren't sufficient to cause tunneling. This is simultaneously reassuring and troubling.
Reassuring because it tells us we're not in immediate danger. The vacuum is stable against the kind of random, high-energy events that occur naturally throughout the cosmos. Whatever the precise configuration of the Higgs potential, it's stable enough that cosmic rays haven't destroyed the universe. Troubling because it doesn't eliminate the possibility of spontaneous vacuum decay through pure quantum tunneling without any trigger at all. The cosmic ray argument only constrains vacuum configurations where high energies can trigger decay. It says nothing about the probability of spontaneous quantum tunneling from the false vacuum to the true vacuum. Think of it this way. Cosmic rays test whether you can knock the ball out of the bowl by hitting it with high-energy particles. The fact that 10 to the 60 collisions haven't knocked it out tells us the bowl has high enough walls to withstand those impacts. But it doesn't tell us whether the ball can quantum tunnel through the bottom of the bowl, appearing spontaneously on the floor below without ever being hit by anything. Those are two separate processes governed by different physics. For vacuum decay through quantum tunneling without any external trigger, the relevant timescale is determined by the action of the bounce solution, which depends on the details of the Higgs potential at all energies. And those calculations give lifetimes of 10 to the 100 years or more, far longer than the 13.8 billion years the universe has existed. So the cosmic ray argument and the spontaneous decay calculations are perfectly consistent. The vacuum hasn't decayed spontaneously in 13.8 billion years because the probability over that time frame is vanishingly small, perhaps one chance in 10 to the 90. And cosmic rays haven't triggered decay because the energy threshold for triggering is higher than even the most energetic cosmic rays can achieve. Both can be true, and if both are true, we're safe for timescales far longer than the current age of the universe, but not safe forever. There's a subtlety here worth exploring. When I say cosmic rays have energies of 10 to the 20 eV, that's the kinetic energy of the particle, the energy associated with its motion through space. But vacuum decay depends on energy density in the Higgs field specifically. A cosmic ray collision creates a shower of particles, releasing energy over a region of space perhaps a meter across. This energy is distributed among thousands or millions of secondary particles: pions, kaons, protons, neutrons, photons, neutrinos. The energy density in any one location, and specifically the energy density coupled to the Higgs field, might be far lower than the total collision energy suggests. Triggering vacuum decay likely requires creating a coherent excitation of the Higgs field itself, getting the field value to fluctuate up near the barrier, across some extended region of space, so that quantum tunneling becomes probable. Random particle collisions, even very high-energy ones, might not achieve this. The energy might be in the wrong form, or distributed too diffusely, or coupled to the wrong fields. This is one reason why cosmic rays might not trigger vacuum decay, even if their total energy seems sufficient. The energy isn't delivered to the Higgs field in the right way. But this raises another question. Are there astrophysical processes that could deliver energy to the Higgs field in the right way? Colliding neutron stars create conditions of extraordinary density and temperature. Temperatures exceeding 10 to the 12 Kelvin, densities higher than atomic nuclei. In these conditions, all the fundamental forces are active. Particles are created and destroyed by the billions, and the Higgs field fluctuates wildly. The LIGO Gravitational Wave Observatory detected its first neutron star collision in August 2017. The event, designated GW 170817, occurred about 130 million light-years away in the galaxy NGC 4993. LIGO detected the gravitational waves from the merger, while telescopes around the world observed the electromagnetic radiation, gamma rays, X-rays, visible light produced in the aftermath. The collision released energy equivalent to about 5% of the total mass energy of the Sun, emitted over the course of a few seconds. The peak energy release rate exceeded the luminosity of all the stars in the observable universe combined. Could such an event trigger vacuum decay? Probably not. The energies involved, while enormous by human standards, are still far below the Planck scale, where vacuum stability becomes truly questionable. And neutron star collisions have been occurring throughout cosmic history. There's an estimated 100 per year just in our galaxy alone, though most are too distant to detect. If neutron star collisions could trigger vacuum decay, it likely would have already happened somewhere in the universe's 13.8 billion year history. But probably not, and likely are not certainly not, and definitely not. There's residual uncertainty. We can't absolutely rule out the possibility that some exotic astrophysical event, perhaps something we haven't observed yet, perhaps something involving physics we don't fully understand, could create conditions that make vacuum decay more probable. The cosmic ray argument provides powerful evidence for vacuum stability over cosmic timescales, but it's not absolute proof. It's a constraint, not a guarantee. And constraints, even very strong ones, leave room for unlikely possibilities. The universe has survived 13.8 billion years. That tells us something important, but it doesn't tell us the universe will survive the next 13.8 billion years, or the next 13.8 trillion years, or the next Google years. Probability is not protection. Past survival does not guarantee future survival. and when the stakes are the continued existence of everything, even small uncertainties take on enormous weight.
The evidence extends beyond particle physics and contemporary cosmic ray observations into the deep history of the cosmos itself, to events that occurred in the first fraction of a second after the Big Bang. According to our best cosmological models, validated by decades of observations from satellites like COBE, WMAP, and Planck, the universe underwent a period of exponential expansion called cosmic inflation when it was less than 10 to the minus 30 seconds old. During inflation, space itself expanded faster than light, not by objects moving through space, but by space itself stretching. The expansion was so rapid that the distance between any 2 points would double every 10 to the minus 37 seconds or so. In less than a blink of an eye, a region of space smaller than an atom would expand to billions of light years across. This sounds like science fiction, but the evidence for inflation is compelling. Inflation explains why the universe is so uniform in all directions. Regions that are now separated by billions of light years were once close enough to equilibrate thermally. It explains why space is so flat. Exponential expansion would flatten out any initial curvature. And it explains the origin of cosmic structure. Tiny quantum fluctuations during inflation were stretched to cosmic scales, becoming the seeds that eventually grew into galaxies. But inflation also created conditions of extraordinary energy density and extreme quantum fluctuation. During inflation, the universe was filled with inflationary energy, the energy density associated with whatever field, called the inflaton, was driving the exponential expansion. This energy density was enormous, comparable to the vacuum energy of the false vacuum we discussed earlier, but much larger in total because the universe was smaller and denser. The temperature during inflation was likely around 10 to the 15 GeV or higher, billions of times hotter than the center of the sun, hot enough that particles and antiparticles were constantly being created and annihilated from pure energy. In these conditions, the Higgs field would not have been sitting calmly at its vacuum value. It would have been fluctuating wildly, driven by quantum uncertainty and thermal energy. The field value at any point in space would have varied randomly, exploring different values across microscopic distances. Now here's the critical question. During this period of wild fluctuation and extreme energy, why didn't the Higgs field tunnel to the true vacuum? Remember, quantum tunneling becomes more likely at high energies because the effective barrier height is reduced. During inflation, with energies of 10 to the 15 GeV or more, the Higgs field would have been pushed to values far from its current vacuum value. It would have spent time exploring the energy landscape, including regions near the barrier separating false vacuum from true vacuum. If vacuum decay were easy, it should have happened then. The universe would have decayed to the true vacuum in the first 10 to the minus 30 seconds of its existence, long before stars, planets, or life could form. Yet here we are. The universe survived inflation without decaying. This is sometimes called the primordial vacuum decay problem, and it's one of the most important clues we have about the stability of the vacuum. Several solutions have been proposed. One possibility is that during inflation, the Higgs field was stabilized by its coupling to the inflaton. The inflaton's large energy density might have modified the effective potential for the Higgs field, creating a barrier or a different valley structure that prevented decay. Imagine the Higgs field as a ball rolling on a landscape. Normally, this landscape has hills and valleys determined by the Higgs potential, but during inflation, the enormous energy density of the inflaton field modifies this landscape, like adding an extra force that changes where the valleys are or creating new barriers.
In this modified landscape, the Higgs field might have been held in a configuration that prevented tunneling to the true vacuum, even though tunneling would be possible in the landscape we experience today. This is an active area of research. Physicists have written dozens of papers exploring how different inflationary models affect Higgs stability. The details depend on how the Higgs field couples to the inflaton, what the inflaton potential looks like, and what energy scale inflation occurred at. Another possibility, more radical, is that vacuum decay did occur during inflation, perhaps many times. But here's the key. During inflation, space was expanding exponentially fast. Imagine a vacuum decay bubble forms. The bubble starts to expand at the speed of light, but the space around the bubble is also expanding, and during inflation, it's expanding faster than light.
The result? The bubble gets swept away by the expansion before it can grow large enough to affect significant regions. It's like trying to blow a soap bubble in a hurricane. The bubble forms, but is immediately swept away and dissipated. In this scenario, the early universe was full of vacuum decay bubbles constantly forming and being diluted by inflation. The bubbles never got large enough to coalesce and consume the universe because inflation was expanding space faster than the bubbles could grow. This is speculative, but not implausible. Some cosmologists, including Alexander Vilenkin at Tufts University and Andre Lind at Stanford, have explored models where vacuum decay during inflation creates a kind of quantum foam, a frothy structure of different vacuum patches, all being stretched and separated by exponential expansion. When inflation ended, when the inflaton field decayed and the universe transitioned to the radiation-dominated hot Big Bang era we understand better, the wild fluctuations stopped. The Higgs field settled into its current vacuum value, and we've been sitting in that vacuum ever since. The fact that the universe survived inflation provides a crucial constraint. The Higgs potential must be such that either the barrier to vacuum decay was high enough that even the extreme energies during inflation weren't sufficient to trigger decay frequently, or the coupling between the Higgs and the inflaton stabilized the Higgs field during inflation, preventing decay, or decay occurred but was harmless because inflationary expansion swept the bubbles away faster than they could grow. Each scenario has different implications for current vacuum stability. If option 1 is correct, the barrier was simply high enough to survive inflation, then current vacuum stability is robust. The barrier that survived 10 to the 15 GeV energies during inflation will certainly survive the much lower energies present in the universe today. If option 2 is correct, stabilization by the inflaton, then we need to know more about inflationary physics to determine current stability. The Higgs field today doesn't couple to an inflaton. Inflation ended long ago, so the stabilization mechanism is gone. The vacuum might be less stable now than it was during inflation. If option 3 is correct, decay during inflation was diluted by expansion, then vacuum decay remains possible today, but without inflation's exponential expansion to dilute it, a decay bubble forming now would grow without limit. Observations from the Planck satellite provide crucial data. Launched in 2009, Planck mapped the cosmic microwave background radiation, the afterglow of the Big Bang, with unprecedented precision. This radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. But encoded in tiny temperature fluctuations in this radiation is information about conditions during inflation billions of years earlier. The Planck results, published in 2018, constrained the energy scale of inflation to be around 10 to the 15 to 10 to the 16 GeV, coincidentally right in the range where Higgs vacuum stability calculations become problematic. This is uncomfortably close to the energy scales where the Higgs field develops its second minimum.
Some physicists see this as a hint of new physics. Perhaps the Higgs field really was coupled to the inflaton, and this coupling helped determine inflation's energy scale. Others see it as a coincidence that demands explanation but doesn't yet have one. What we know for certain is that the universe existed at these energy scales for at least 10 to the minus 30 seconds during inflation and survived. The Higgs field was buffeted by enormous energies and wild quantum fluctuations and didn't decay to the true vacuum, or if it did, the decay was harmless. This is evidence, not proof, but evidence that the vacuum is reasonably stable, at least stable enough to survive the most extreme conditions the universe has experienced since the Planck epoch. But it's not definitive. The conditions during inflation were different from conditions today. The expansion rate was different, the field configurations were different, the coupling to other fields was different. We cannot directly observe what the Higgs field was doing during inflation. We can only infer it from theoretical calculations and indirect observations of the microwave background. And those calculations contain uncertainties. We don't know exactly what inflation was, what field drove it, what potential it had, how it coupled to the Higgs. We have models, well motivated by theory and consistent with observations, but we don't have definitive knowledge. So the survival of the universe through inflation is evidence for vacuum stability, but not conclusive proof. It rules out the most unstable vacuum configurations, but leaves room for metastability with long lifetimes. The early universe was a crucible of extreme energies and wild quantum fluctuations. The Higgs field survived that crucible. But survival of past trials doesn't guarantee survival of future ones, especially when future trials might involve pure quantum tunneling over timescales of googles of years rather than high-energy fluctuations over fractions of a second.
Perhaps the most remarkable discovery involves something physicists call vacuum energy, or the cosmological constant. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating. This was completely unexpected. Gravity should slow expansion, not accelerate it. The discovery won the Nobel Prize in 2011. The acceleration is caused by something called dark energy, a form of energy that fills all of space uniformly and has negative pressure, causing space itself to expand faster over time. The simplest explanation for dark energy is that it's the energy of the vacuum itself. But when physicists calculate what the vacuum energy should be based on quantum field theory, they get a number that's 10 to the 120 times larger than what we observe. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Here's where it connects to vacuum decay. The observed vacuum energy represents the energy of our current false vacuum state. If the universe decayed to the true vacuum, the vacuum energy would be different, likely much more negative. The specific value of the cosmological constant in our universe appears incredibly fine-tuned. If it were slightly larger, the universe would have expanded too quickly for galaxies to form. If it were negative, the universe would have collapsed in a big crunch. Some physicists, like Steven Weinberg and Nobel laureate Frank Wilczek, have argued that we observe the value we do because it's one of the few values consistent with the existence of observers. In a multiverse where different regions have different vacuum energies, only those regions with values allowing galaxy formation and life would contain beings asking why the value is what it is. But this represents just one piece of a much larger puzzle hidden in the quantum structure of space-time itself.
What scientists found next challenged everything we thought we understood about the stability of physical law. In the decades since the Standard Model was formulated in the 1970s, physicists expected that new physics, new particles, new forces, new phenomena would appear at high energies. These new phenomena would modify the Standard Model's predictions and potentially stabilize the vacuum. Theoretical frameworks like supersymmetry predicted partners for every known particle. String theory suggested extra dimensions of space. Grand unified theories proposed that all forces merge at high energy. But the Large Hadron Collider found nothing. From 2010 to 2018, the LHC collided protons at higher energies than ever before, creating millions of particle interactions. The data was analyzed by thousands of physicists searching for any hint of physics beyond the Standard Model. They found the Higgs boson exactly as predicted, but no supersymmetric particles, no extra dimensions, no hints of new forces or phenomena. The Standard Model, originally thought to be merely a low-energy approximation of a more complete theory, appears to work perfectly all the way up to energies of at least 14 trillion electron volts, perhaps far beyond. This is profoundly troubling for vacuum stability. Supersymmetric particles, if they existed, would contribute to the Higgs potential in ways that could stabilize the vacuum. Their absence means the vacuum is more precarious than many hoped. In 2018, physicist Matthew McCullough from CERN published an analysis showing that without new physics to stabilize it, the Standard Model vacuum appears to sit right on the edge between stability and metastability. The measured values of particle masses are close to the boundary where the vacuum transitions from stable to metastable. This remarkable discovery involves a kind of cosmic coincidence. Why should the Higgs mass be 125 GeV rather than 120 or 130? Why should the top quark mass be 173 GeV rather than 170 or 176? Each of these values, independently, seems arbitrary, yet together they place us in this precarious state. Some physicists call this the criticality of the Standard Model. The parameters appear fine-tuned to place the universe right at the edge of stability. Is this a clue, a coincidence, or something deeper we don't yet understand?
The most disturbing evidence comes from the intersection of quantum mechanics and general relativity. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. But in 1974, Stephen Hawking discovered that black holes aren't entirely black. Quantum effects near the event horizon cause black holes to radiate particles, a phenomenon called Hawking radiation. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the temperature is tiny, billionths of a degree above absolute zero. But as a black hole evaporates through Hawking radiation, it gets smaller and hotter. In the final moments of a black hole's evaporation, its temperature soars to extraordinary values. When the black hole reaches microscopic size, around the Planck mass of about 20 micrograms, its temperature exceeds 10 to the 32nd Kelvin. The Hawking radiation at this point carries energies approaching the Planck scale. These are exactly the energies where vacuum decay becomes possible. In 2013, physicists Piero Berta, Ruth Gregory, and Ian Moss published a startling paper in Physical Review Letters. They calculated that small black holes could seed vacuum decay bubbles. The intense curvature of spacetime near a microscopic black hole, combined with the extreme energies of Hawking radiation, creates conditions favorable for quantum tunneling. Their calculations suggest that black holes below a certain mass, around 10 to the 5th kilograms, about the mass of a large mountain, could trigger vacuum decay with non-negligible probability. Do such black holes exist? Primordial black holes, formed in the first second after the Big Bang from density fluctuations, could span a wide range of masses. While we haven't detected any definitively, they remain a possibility. If primordial black holes exist in this critical mass range, they could be ticking bombs scattered throughout the universe. Even more troubling, every black hole eventually evaporates to this dangerous size.
Stellar mass black holes will take 10 to the 67th years to evaporate completely, but when they do, they'll pass through the dangerous mass range where vacuum decay becomes possible. The universe might be safe for now, but in the far future, as black holes evaporate, the risk of vacuum decay could increase dramatically.
Recent breakthroughs suggest a connection between vacuum decay and the multiverse hypothesis. If eternal inflation is real, the idea that inflation never completely ends but continues in different regions of space, then the universe we observe is just one bubble in an eternally inflating sea of space. Different bubbles could have different vacuum states, different laws of physics, different values of fundamental constants. In this framework, vacuum decay takes on new meaning. When a region of false vacuum decays to true vacuum, it creates a new bubble universe with different physics. This bubble expands at light speed, but the space around it continues to inflate even faster. The result is an ever-expanding multiverse with countless bubble universes, each with its own vacuum state. Physicist Alexander Vilenkin at Tufts University has developed mathematical models of this process. His calculations, published in multiple papers between 2000 and 2020, show that in an eternally inflating universe, vacuum decay becomes not just possible, but inevitable. It happens continuously, creating new bubble universes throughout the multiverse. From this perspective, our universe, our bubble, exists in a false vacuum simply because false vacuum bubbles can form in an inflating multiverse. We don't observe the true vacuum because inside true vacuum bubbles, inflation might not occur, or the laws of physics might not allow complex structures like atoms, stars, and life. This is the anthropic principle taken to its logical extreme. We observe what we observe because only in universes like ours can observers exist. But there's a darker implication. If we are in a false vacuum bubble surrounded by eternally inflating space, other bubbles could be forming constantly in the inflating region beyond our cosmic horizon. Some of these bubbles might be true vacuum bubbles. If a true vacuum bubble forms near enough to our false vacuum bubble, the two bubbles could collide. The collision would leave distinctive patterns in the cosmic microwave background radiation, cold spots, or anomalies in the temperature distribution. In 2010, researchers at University College London analyzed Planck satellite data, looking for exactly these signatures. They found several candidate cold spots that could potentially be the result of bubble collisions. The results are controversial and remain debated, but the fact that we're looking for evidence of other universes colliding with ours and finding possible candidates represents an extraordinary development in cosmology. The evidence extends beyond particle physics and cosmology into the realm of quantum gravity and the fundamental structure of reality.
At the Planck scale, 10 to the 19th GeV, space and time themselves become quantum mechanical. The smooth space-time of general relativity breaks down into a foam of quantum fluctuations. Our theories of physics, developed for lower energies, no longer apply. This is both a blessing and a curse for vacuum stability calculations. It's a blessing because it means the Higgs potential might be modified at high energies by quantum gravity effects we can't currently calculate. These modifications could potentially stabilize the vacuum, preventing decay even if the standard model alone predicts metastability. It's a curse because it means we fundamentally cannot predict with certainty what happens at the highest energies. The vacuum might be stable, it might be metastable, or quantum gravity introduce entirely new physics that changes the question completely. In 2019, a research team led by John Ellis at CERN published calculations incorporating possible quantum gravity corrections to the Higgs potential. Their results showed that depending on how quantum gravity modifies the standard model at high energies, the vacuum could be stabilized or rendered even more unstable.
We stand at the edge of our theoretical knowledge, peering into an abyss where the laws of physics themselves become uncertain. And yet the question remains: metastable or stable? Safe or doomed? The answer may determine the fate of everything that exists.
To truly grasp what vacuum decay means, we must understand the Higgs potential in detail. Imagine the Higgs field as a value assigned to every point in space, a number that determines how particles acquire mass. The Higgs potential is a function that tells us the energy associated with any particular value of the Higgs field. In the simplest models, this potential has the shape of a Mexican hat or wine bottle bottom, high energy at zero field value, dropping down to a circular trough with a slight bump in the middle. The Higgs field naturally rolls down to the trough, which represents the vacuum state of the universe. But this is an approximation. When you include quantum corrections, contributions from virtual particles popping in and out of existence, the shape of the potential changes. At high field values, corresponding to high energies, quantum corrections from top quarks become important. The top quark's contribution is negative. It makes the potential curve downward. If this negative contribution is strong enough, it can overwhelm the positive contributions from other particles, causing the potential to develop a second minimum at high field values. This second minimum is the true vacuum. It has lower energy than our current false vacuum, but there's a barrier between them, a hill in the potential that the field would need to climb to reach the true vacuum. Classically, the Higgs field is trapped, but quantum mechanically it can tunnel through the barrier. The rate of tunneling depends exponentially on the barrier's height and thickness. Higher barriers mean exponentially longer tunneling times. This is why the vacuum can be metastable for googles of years. The barrier is high enough that tunneling is extraordinarily rare. But rare is not impossible. When physicists at the Mines Institute for Theoretical Physics calculated the tunneling rate in 2015, they found that the lifetime of the false vacuum could range from 10 to the 100 to 10 to the 600 years, depending on the precise values of particle masses and the unknown physics at the Planck scale. Even at the low end of this range, we're safe for timescales far longer than the current age of the universe. But the uncertainty is enormous, a factor of 10 to the 500, which is almost incomprehensibly large.
Not all physicists agree on the interpretation of these results. One school of thought, represented by theorists like Joseph Licken and Frank Wilczek, takes the calculations at face value. The standard model predicts metastability. Observations confirm the necessary particle masses. Therefore, we live in a false vacuum that will eventually decay. The timescale is long enough that it poses no practical threat, but the principle remains. Our universe is temporary. Another perspective, championed by researchers like Steven Weinberg and Leonard Susskind, emphasizes the multiverse interpretation. If eternal inflation creates countless bubble universes with different vacuum states, we shouldn't be surprised to find ourselves in a metastable vacuum. It's simply where complex structures and observers can exist. The vacuum's metastability is not a problem to solve, but a fact to accept as part of the anthropic landscape. A third viewpoint, held by researchers including particle physicist Gianfrancesco Giudice at CERN, suggests that the apparent metastability is a hint of new physics. The standard model might be incomplete in subtle ways. Perhaps there are new particles just beyond the LHC's energy reach that stabilize the vacuum. Perhaps quantum gravity effects kick in earlier than expected. Perhaps the Higgs boson itself is not elementary, but composite, made of more fundamental particles. Each interpretation has different implications.
If the standard model is complete and the vacuum is metastable, we live in a universe with an expiration date, distant but definite. If the multiverse interpretation is correct, vacuum decay is constantly occurring throughout the larger cosmos, creating new universes with different physics. Our universe is one bubble among countless others. If new physics exists just beyond our current reach, the next generation of particle accelerators might discover it, fundamentally changing our understanding of vacuum stability. Leading physicists and astronomers believe different things, and this diversity of viewpoints reflects the genuine uncertainty in our current knowledge.
This forces us to reconsider fundamental assumptions about the nature of physical law. We tend to think of the laws of physics as eternal and unchanging. The speed of light is constant, the strength of gravity is fixed, the electron's charge is immutable. But if vacuum decay is possible, these laws are merely the rules that happen to apply in our current vacuum state. In the true vacuum, everything could be different. The speed of light might have a different value. The strength of fundamental forces might change. Particles might have different masses or not exist at all. The laws of physics would not be laws in any absolute sense, but rather local bylaws, rules that apply in our neighborhood of the cosmic landscape, but nowhere else. This has profound implications for our understanding of why the universe looks the way it does. Why is the electron exactly 1/1836th the mass of the proton? Why does the electromagnetic force have precisely the strength it does? Why are there 3 generations of quarks and leptons? These questions have puzzled physicists for decades. But if physical constants can vary between vacuum states, the answer might be anthropic. We observe the values we do because they're among the few values compatible with the existence of observers. Philosopher Nick Bostrom at Oxford University has written extensively about these implications. If the fundamental constants of nature are not determined by any deeper principle, but vary across different vacuum states, then our existence in a vacuum state with observer-compatible constants is inevitable, but also utterly contingent. We're not special. We're simply one of countless possibilities that happened to allow complexity, chemistry, life, and consciousness. This is simultaneously humbling and terrifying. Humbling because it strips away any notion of cosmic significance to our existence. Terrifying because it implies that everything we are, everything we've built, everything we value, depends on quantum vacuum structure that could change at any moment. The philosophical implications extend from physics into metaphysics, from science into existentialism. What technologies might help solve the remaining mysteries? The Future Circular Collider, proposed by CERN for construction in the 2040s, would collide particles at energies 7 times higher than the LHC. With collision energies reaching 100 TeV, it could discover new particles that stabilize the vacuum or provide evidence for supersymmetry, extra dimensions, or other beyond standard model physics. If supersymmetrical particles exist with masses and the range accessible to the FCC, their discovery would fundamentally change vacuum stability calculations. Supersymmetry introduces new quantum corrections to the Higgs potential that could eliminate the second minimum, stabilizing the false vacuum. But building the FCC will cost tens of billions of dollars and take decades, and there's no guarantee it will find anything beyond the standard model. The LHC already ruled out the most optimistic supersymmetry scenarios. Another approach focuses on precision measurements. The Large Hadron Collider is continuing to run through the 2030s, and physicists are working to measure the Higgs mass, top quark mass, and other standard model parameters with ever greater precision. Small changes in these values shift the vacuum stability calculations. Current uncertainties in the top quark mass alone introduce factors of 10 or 100 in the calculated vacuum lifetime.
If the top quark turns out to be slightly lighter than currently measured, the vacuum might be absolutely stable. Slightly heavier, and metastability becomes certain. The high-luminosity LHC upgrade, scheduled to begin operation in 2029, will produce 10 times more collision data than the current LHC. This should reduce measurement uncertainty significantly. Gravitational wave observatories offer an entirely different approach. The LIGO and Virgo detectors, which made the first detection of gravitational waves in 2015, are sensitive to space-time ripples from colliding black holes and neutron stars. Future detectors like LISA, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will observe gravitational waves from the early universe. If cosmic inflation occurred, it should have produced a background of gravitational waves. The precise characteristics of this gravitational wave background depend on inflation's energy scale and dynamics, information that could constrain models of the early universe and provide clues about the Higgs field's behavior during inflation. If vacuum decay occurred during inflation and was prevented from consuming the universe only by inflation's exponential expansion, this might leave signatures in the primordial gravitational wave spectrum.
What might we discover in the coming decades? One possibility is the discovery of new particles at high energies. If the next generation of colliders finds supersymmetric particles, extra dimensions, or other new physics, it would completely reshape our understanding of vacuum stability. The discovery of supersymmetry would be particularly significant. Supersymmetric particles contribute to the Higgs potential in ways that could stabilize the vacuum. If supersymmetry exists at accessible energies, the vacuum might be stable after all, and our universe has no expiration date. Another possibility is increasingly precise measurements that definitively establish whether the vacuum is metastable or stable. With better measurements of particle masses and improved theoretical calculations, we might nail down the vacuum lifetime to within a few orders of magnitude. If the calculations converge on lifetimes shorter than 10 to the 100 years, it would confirm metastability. If they show lifetimes longer than the age of the universe times the size of the universe in Planck volumes, roughly 10 to the 180 years, metastability becomes effectively irrelevant. The universe is stable for all practical purposes. A third possibility involves cosmological observations. The Vera Rubin Observatory, beginning operations in 2025, will survey the entire visible sky every few nights, creating a time-lapse movie of the universe. It will detect supernovae, map dark matter, and search for any anomalous signals that might indicate unusual astrophysical phenomena. Could we detect a vacuum decay bubble approaching? Probably not directly. The bubble wall moves at light speed, giving no warning. But if vacuum decay has occurred elsewhere in the universe, the bubble might be visible at great distances, appearing as a region of altered physics that looks different from our own. The James Webb Space Telescope and future observatories might detect anomalies in distant galaxies that could be interpreted as evidence of different vacuum states. Unusual spectral lines, unexpected particle physics, or violations of what we consider fundamental constants. These observations remain speculative, but they represent the kind of unexpected discoveries that could revolutionize our understanding.
The vacuum stability question connects to some of the deepest mysteries in physics. The hierarchy problem asks why the Higgs mass is so much smaller than the Planck mass. Naively, quantum corrections should drive the Higgs mass up to Planck scale values, yet we measure it at 125 GeV, 17 orders of magnitude smaller. This requires extraordinary fine-tuning or some mechanism that protects the Higgs mass. Vacuum stability is intimately connected to this problem. The same quantum corrections that create the hierarchy problem also determine the shape of the Higgs potential at high energies, which in turn determines vacuum stability. Solutions to the hierarchy problem, like supersymmetry or compositeness of the Higgs boson, would also impact vacuum stability. A composite Higgs would have different quantum corrections than an elementary one, potentially changing the vacuum stability calculations entirely. The cosmological constant problem, why the vacuum energy is 120 orders of magnitude smaller than theoretical predictions, also connects to vacuum stability. The vacuum energy we observe is the energy of our current false vacuum state. In the true vacuum, the vacuum energy would be different. Some theorists speculate that the true vacuum has exactly zero cosmological constant, while our false vacuum has a small positive value that causes the accelerated expansion we observe. This would elegantly solve the cosmological constant problem, but it would confirm we're in a false vacuum doomed to eventually decay. The question of what happens at the Planck scale, where quantum gravity becomes important, underlies everything. Until we have a working theory of quantum gravity, whether string theory, loop quantum gravity, or something else, we cannot definitively calculate what happens to the vacuum at the highest energies. Recent breakthroughs in string theory suggest that the landscape of possible vacuum states might contain 10 to the 500 different vacua, each with different physics. If this is correct, vacuum decay takes on new significance. It's the mechanism by which the universe explores the landscape, sampling different possible laws of physics. What this means for us, for humanity, for our place in the cosmos is profound. We've built civilizations, developed technology, created art and music and literature, launched ourselves into space, all while sitting in a vacuum state that might be temporary. Everything we are, everything we've accomplished, exists in a bubble that could, at any moment, be consumed by a wave of altered physics traveling at the speed of light. Yet this knowledge should not lead to despair. The vacuum's lifetime, even if metastable, is so long that it dwarfs all human timescales. The sun will die in 5 billion years. Galaxies will fade in trillions of years. The last stars will burn out in 100 trillion years. But vacuum decay, if it happens, lies googles of years in the future, timescales that make even the heat death of the universe look imminent by comparison. We are safe. Our children are safe. Countless generations of our descendants are safe. But the universe itself, on the longest timescales imaginable, might not be eternal after all.
The most profound implications emerge when we consider what vacuum decay tells us about the nature of reality itself. We think of the universe as a place, a vast expanse of space filled with matter and energy, governed by fixed laws of physics. But vacuum decay suggests a different picture. The universe is not a place with laws. The universe is a field configuration, a specific arrangement of quantum fields that happens to support the existence of particles, forces, and structures we call matter. This configuration, our vacuum state, is not unique. It's not even optimal. It's simply one possibility among countless others, and it happens to be relatively stable. But relatively stable is not eternal. In the true vacuum, the Higgs field would have a different value. This would change the masses of all fundamental particles. The electron might be heavier or lighter. Quarks might have different masses, changing the properties of atomic nuclei. The fine structure constant, which determines the strength of electromagnetic interactions, might be different. Chemistry would be impossible. Atoms as we know them couldn't form. Molecules couldn't exist. Stars couldn't fuse hydrogen into helium. Planets couldn't form. Life would be impossible. The true vacuum would be a dead universe, sterile and empty, governed by physics hostile to complexity. This raises a question. Why do we exist in a false vacuum that supports life, rather than the true vacuum that doesn't?
The anthropic answer is unsatisfying but unavoidable, because only in false vacua like ours can observers exist to ask the question. The true vacuum might be more stable, more fundamental, lower in energy, but it's empty. No consciousness arises there to wonder why. We exist because we can exist, and we can exist only in the rare vacuum states where the laws of physics permit complexity. This is both enlightening and devastating. Enlightening because it answers why questions that seemed unanswerable. Devastating because it strips purpose from the cosmos. The universe is not designed for us. The laws of physics are not tuned for our benefit. We simply happen to exist in one of the rare corners of the cosmic landscape where existence is possible. And that corner might not last forever.
What would vacuum decay actually look like? Somewhere, at some random point in space, a quantum fluctuation occurs. The Higgs field, which has been stable for billions of years, suddenly tunnels through the barrier separating false vacuum from true vacuum. A bubble forms, a tiny sphere, perhaps no larger than a proton, where inside the Higgs field has dropped to its true value. Inside this sphere, physics is different. But the bubble doesn't stay tiny. The true vacuum has lower energy than the false vacuum, and this energy difference drives the bubble to expand. The bubble wall, the boundary between true and false vacuum, races outward at the speed of light. As it expands, it converts false vacuum to true vacuum. The Higgs field drops. Particle masses change, the fundamental constants shift. Inside the bubble, atoms cannot hold together. Electrons and quarks have wrong masses. Nuclear forces have wrong strengths. Chemistry fails. Matter dissolves. Everything in the bubble's path is annihilated, not destroyed by heat or impact, but fundamentally transformed at the level of physical law. Planets, stars, galaxies, all converted to whatever forms of matter can exist in the true vacuum. Presumably just scattered particles and radiation, no stable structures, no complexity. The bubble expands forever. Because it moves at light speed, it can never slow down or stop. It consumes everything in its path, rewriting the laws of physics from false vacuum to true vacuum. Could we detect it approaching? No. Light from the bubble wall travels at light speed. The wall itself travels at light speed. By the time we saw it, we'd already be inside it. There would be no warning, no time to react, no possibility of escape. Could we escape by traveling away from the bubble at near light speed? No. The bubble expands at exactly light speed. Nothing can outrun it. Anywhere you could travel to, the bubble would reach simultaneously. Could we survive inside the bubble by somehow adapting to the new physics? No. The physics inside doesn't support life. Complex molecules cannot form. Information cannot be stored or processed. Consciousness cannot exist. Death would not be instantaneous. It would be instantaneous across all space as the bubble passes, but subjectively, from the perspective of someone on the boundary, what would you experience? As the bubble wall approaches at light speed, you would see nothing unusual. The wall is traveling at light speed, so no light from it reaches you until it hits you. At the moment the wall passes through your location, the laws of physics change. Atoms destabilize, molecular bonds break, neural patterns dissolve. Consciousness ceases, not because your brain is destroyed by heat or impact, but because the physics necessary for consciousness no longer exists. You would not experience pain. You would not experience fear. You would not experience anything. The substrate of experience itself would be rewritten out of existence. This is what vacuum decay means. Not death, not destruction, unmaking.
what does the evidence suggest about our actual future? Scenario 1. The vacuum is actually stable. The calculations suggesting metastability are wrong because of unknown physics at high energies. Quantum gravity effects, new particles, or some other phenomenon stabilizes the Higgs potential. The universe is eternal, at least with respect to vacuum decay. We're safe forever. Probability, based on current evidence, perhaps 30%. The standard model calculations seem robust, but our ignorance of quantum gravity introduces large uncertainties. Scenario 2. The vacuum is metastable, but the decay time is so long, 10 to the 500 years or more, that it's irrelevant on any conceivable timescale. The universe will suffer heat death, black hole evaporation, and the final fading of all stars trillions of years before vacuum decay becomes probable. Effectively, we're safe. Probability, perhaps 50%. This matches what calculations suggest if there's no new physics beyond the standard model. Scenario 3. The vacuum is metastable with a relatively short lifetime, say 10 to the 100 years. This is still vastly longer than the current age of the universe, but it's short enough that vacuum decay represents the ultimate fate of the cosmos. After the stars die, after black holes evaporate, the universe will eventually be consumed by a vacuum decay bubble. Total destruction, but in the unimaginably far future. Probability, perhaps 15%. Possible if the standard model is complete and our measurements are near the true values. Scenario 4. Vacuum decay has already occurred somewhere in the universe, and a bubble is expanding toward us right now. We won't detect it until it arrives. Could be tomorrow, could be in a billion years, could be never if the bubble formed far enough away that the expansion of space carries it away from us faster than it can approach. Probability, very low, perhaps 1%. The universe has existed for 13.8 billion years without vacuum decay occurring in our observable region, suggesting the rate is very low. Scenario 5. The multiverse interpretation is correct. Vacuum decay occurs constantly throughout eternally inflating space, creating bubbles with different physics. Our universe is one bubble among countless others. Vacuum decay is both inevitable on cosmic scales and irrelevant to us because it creates rather than destroys. It creates new universes with new physics. Probability, impossible to quantify, but growing acceptance among cosmologists, perhaps 20 to 30%. The most likely future, based on current evidence, is Scenario 2. We live in a metastable vacuum that will last far longer than any other relevant timescale in the universe. Vacuum decay is real, possible, and inevitable, but so far in the future that it poses no threat to anything we care about. But the uncertainty remains enormous. We cannot predict with certainty what unknown physics at the Planck scale might do. We cannot measure all relevant parameters with perfect precision. We cannot observe the entire universe to confirm vacuum decay hasn't started somewhere beyond our horizon. We live with uncertainty, and that uncertainty concerns the most fundamental question possible. Will the universe exist forever, or does it have an expiration date written into its quantum structure? The evidence points toward an answer, but cannot provide certainty. And in that gap between evidence and certainty lies the profound mystery of our existence.
We began this journey 3 hours ago with a simple but terrifying question. Could the universe end in an instant, consumed by a bubble of altered physics traveling at light speed, rewriting the laws of nature and rendering our existence impossible? The answer, as we've discovered through examining decades of theoretical work and experimental data, is yes, it could. But could requires careful qualification. The mathematics of quantum field theory
tested to extraordinary precision in particle accelerators around the world, predicts that our universe exists in what's called a metastable state, a false vacuum. The Higgs field, which gives particles their mass and pervades all of space, sits in a local minimum of its potential energy landscape, not the absolute deepest minimum. This configuration is stable against small perturbations. You can't knock the universe out of its false vacuum by hitting it with particles, even very high-energy cosmic rays. We've tested this accidentally through billions of years of cosmic ray bombardment, roughly 10 to the 60th ultra-high energy collisions throughout cosmic history, and the vacuum has survived. But quantum mechanics introduces a possibility that classical physics doesn't allow: quantum tunneling. At any point in space, at any moment in time, there's a probability, vanishingly small but not zero, that the Higgs field could spontaneously tunnel through the energy barrier separating our false vacuum from the true vacuum. When that happens, a bubble forms, a region of space where physics is different, where the laws of nature have changed. And this bubble doesn't sit still. The energy difference between false and true vacuum drives the bubble wall to expand at light speed, forever, consuming everything in its path, converting our universe from one state to another. The expansion is inexorable. There is no defense. There is no warning. Light from the bubble wall travels at the same speed as the wall itself, so by the time you detect it, it's already converted you. There's no moment of awareness, no instant of recognition. The physics that allows consciousness simply stops functioning. This is vacuum decay, and it's not speculation. It emerges from our best-tested theories of fundamental physics. But we've also learned that possible does not mean imminent. The probability of vacuum decay is extraordinarily low. When physicists calculate the half-life of the false vacuum, the time it would take for there to be a 50% chance that decay occurs somewhere in a volume the size of the observable universe, they get numbers between 10 to the 100 and 10 to the 600 years. To give these numbers perspective, 10 to the 100 years is a Google years. The universe is currently 13.8 billion years old. That's 1.38 times 10 to the 10th years. A Google years is 90 orders of magnitude longer. If the current age of the universe were represented by 1 second, a Google years would be longer than the age of the universe by a factor of 10 to the 80th. There literally aren't enough particles in the observable universe to count that high if you used one particle per number. And that's just the low end of the estimate. The high end, 10 to the 600 years, is so incomprehensibly large that the human mind cannot grasp it. It's not just larger than all cosmic timescales, it's larger than any meaningful physical quantity we can measure or imagine. So practically speaking, we're safe. Our children are safe. Our civilization, for as long as it lasts, is safe. The Sun will die in 5 billion years. The Milky Way will collide with Andromeda in 4 billion years. The last stars will burn out in 100 trillion years. Protons might decay, if they do, in 10 to the 35th years. Black holes will evaporate through Hawking radiation in 10 to the 100 years. All of these cosmic endpoints arrive long, long before vacuum decay becomes probable. But, and this is the crucial insight that's driven our entire exploration, improbable is not impossible. Vacuum decay could happen tomorrow. The probability is so low that tomorrow is astronomically unlikely compared to in a Google years. But quantum mechanics deals in probabilities, not certainties. The universe is not guaranteed to last another second, even if the odds of decay in the next second are 1 in 10 to the 100 or less. This is the fundamental uncertainty we live with, encoded in the quantum structure of space-time itself. We've examined the evidence from multiple angles. The measured mass of the Higgs boson at 125.09 GeV, a value that, when plugged into the standard model equations, along with the measured mass of the top quark at 172.76 GeV, predicts metastability. This isn't speculation or interpretation, it's what the mathematics demands. The absence of new physics beyond the standard model at energies up to 14 TeV, tested by the Large Hadron Collider. Supersymmetric particles, extra dimensions, new forces, none have been found. The standard model works perfectly, which means its prediction of metastability stands unchallenged. The cosmic ray observations, showing that 10 to the 60th ultra-high energy particle collisions throughout cosmic history haven't triggered vacuum decay. This tells us the barrier is high enough to survive random high-energy events, but says nothing about spontaneous quantum tunneling. The survival of the universe through cosmic inflation, when energy densities reached 10 to the 15 GeV or higher, and the Higgs field fluctuated wildly. The fact that we exist means the vacuum was stable enough to survive inflation, but inflation's extreme conditions no longer apply. The fine-tuning of fundamental constants, the Higgs mass and top quark mass, appear to place us right at the boundary between stability and metastability. A few % difference in either parameter and the fate of the universe changes from eternal to temporary. The calculations of vacuum lifetime, incorporating all known physics and all measurement uncertainties. These calculations consistently show lifetimes far longer than the current age of the universe, but finite, not infinite. Each piece of evidence independently suggests the same conclusion. We live in a metastable vacuum that will likely last for googles of years, but not forever. This is what we've learned. This is what decades of theoretical development and experimental verification tell us about the ultimate fate of the cosmos.
But enormous questions remain unanswered, and acknowledging these uncertainties is as important as understanding what we know. We don't know what happens at the Planck scale, the energy scale of about 10 to the 19 GeV, where quantum mechanics and general relativity must somehow merge into a theory of quantum gravity that we don't yet possess. At the Planck scale, space-time itself becomes quantum mechanical. The smooth four-dimensional space-time of Einstein's general relativity breaks down into a foam of quantum fluctuations. Distance and time lose their classical meanings. Cause and effect become fuzzy, and we have no working theory that describes this regime. String theory offers one possibility, a framework where fundamental entities are one-dimensional strings vibrating in 10 or 11 dimensions with different vibration modes corresponding to different particles. String theory is mathematically beautiful and potentially incorporates quantum gravity, but it makes few testable predictions and has not been verified experimentally. Loop quantum gravity offers another approach, quantizing space-time itself, treating it as a network of discrete loops and nodes rather than a smooth continuum. This approach is more conservative philosophically, but faces its own mathematical and conceptual challenges. Other approaches exist: causal set theory, asymptotic safety, emergent gravity, but none have achieved the status of confirmed theory. We simply don't know how quantum gravity works. This ignorance matters for vacuum stability because the Higgs potential at very high energies, near the Planck scale, might be modified by quantum gravity effects. These modifications could stabilize the vacuum, eliminating the second minimum entirely. Or they could destabilize it further, making the true vacuum even deeper and the barrier even lower. We can't calculate what we don't understand. Until we have a working theory of quantum gravity, validated by observation or experiment, the vacuum stability calculations contain irreducible uncertainty at the highest energies. We don't know if new physics exists just beyond the reach of our current experiments.
The Large Hadron Collider has probed energies up to 14 TeV with exquisite precision, finding nothing beyond the standard model. But the next generation of particle accelerators, if built, would reach higher energies. The proposed Future Circular Collider, a ring 100 kilometers in circumference encircling Geneva, could reach collision energies of 100 TeV. At these energies, we might discover supersymmetric particles if they exist with masses in this range. We might find evidence of extra dimensions. We might detect new forces or new matter particles. Any of these discoveries would fundamentally change vacuum stability calculations. Supersymmetric particles, in particular, contribute to quantum corrections to the Higgs potential in ways that could stabilize the vacuum. But the FCC hasn't been built yet. It won't be built for decades, if at all. The cost is enormous, perhaps $20 to $30 billion. The technical challenges are formidable. The scientific payoff, while potentially revolutionary, is not guaranteed. And even if we build it and find nothing, that doesn't prove nothing exists at higher energies. It just means nothing exists at accessible energies. There could be new physics at 1,000 TeV, or 10 to the 6th TeV, or the Planck scale, forever beyond our experimental reach. We don't know the precise values of fundamental constants well enough to calculate the vacuum lifetime with certainty. Current measurements of the Higgs mass have uncertainty of about 2%. The top quark mass has uncertainty of about 0.5%. These are incredibly small uncertainties, testament to the extraordinary precision of modern particle physics. But when these uncertainties are fed into the exponential formula for quantum tunneling probability, they translate to factors of 100 or 1,000 or more in the calculated vacuum lifetime. The difference between 10 to the 100 years and 10 to the 300 years is enormous, a factor of 10 to the 200. But both are well beyond the age of the universe, so from a practical standpoint, the difference doesn't matter. However, the uncertainties also mean we can't definitively rule out that the vacuum is absolutely stable. If the true value of the top quark mass lies at the low end of the current uncertainty range, and the Higgs mass at the high end, the calculations shift, and the second minimum might not exist at all. We're living with genuine uncertainty about whether the universe has an expiration date or not.
Ongoing measurements from the high-luminosity LHC, scheduled to begin operation in the late 2020s, will reduce these uncertainties, but they won't eliminate them entirely. There will always be measurement error, always be statistical uncertainty. We don't know if the multiverse is real, if eternal inflation is correct, and the evidence from cosmic microwave background observations is consistent with it, though not conclusive, that our universe is just one bubble among countless others in an eternally inflating sea of space. In this framework, vacuum decay takes on different meaning. Each false vacuum bubble is a universe with its own laws of physics, its own values of fundamental constants. Vacuum decay creates new bubbles with different physics. The multiverse is constantly expanding, constantly creating new universes through both inflation and vacuum decay. If this is correct, then asking when will our universe decay is like asking when will this particular soap bubble in an infinite foam pop. It will happen eventually, but the foam itself continues forever, constantly creating new bubbles. Our existence in a metastable vacuum would be explained by the anthropic principle. We observe what we observe because only in certain rare vacuum states can observers exist. The vast majority of vacuum states might be sterile, empty, hostile to complexity. We find ourselves in a rare pocket where life is possible. But we don't know if this picture is correct. Eternal inflation is a plausible theory consistent with observations, but it's not proven. The multiverse might not exist. Our universe might be all there is.
And if our universe is all there is, then vacuum decay doesn't just mean the end of one bubble, it means the end of everything. We don't know if somewhere, far beyond our cosmic horizon, a vacuum decay bubble has already formed and is racing toward us at light speed. The observable universe extends about 46 billion light-years in all directions. That's how far light has been able to travel in the 13.8 billion years since the Big Bang, accounting for the expansion of space. But the universe is likely much larger. Inflation predicts the universe is at minimum thousands of times larger than the observable portion, possibly infinite. We can't see beyond our cosmic horizon. Light from regions more than 46 billion light-years away hasn't had time to reach us yet. And because the universe is expanding, it never will. Those regions are receding from us faster than light can cross the intervening space. If a vacuum decay bubble formed 50 billion light-years away from us, we would have no way to detect it. The bubble would be expanding at light speed, converting false vacuum to true vacuum, but it would still be beyond our horizon, invisible to all our telescopes and instruments. It might reach us tomorrow, or in a billion years, or never, if the expansion of space carries it away from us faster than it approaches. We cannot know. The universe beyond our horizon is fundamentally unobservable, not due to technological limitations, but due to the finite speed of light and the expansion of space. This is the irreducible uncertainty at the heart of vacuum decay. Even if we perfect our measurements, even if we develop a complete theory of quantum gravity, even if we build accelerators that reach the Planck energy, we can never observe the entire universe to confirm vacuum decay hasn't started somewhere beyond our horizon. These unknowns are not failures of science. They're the frontiers, the boundaries between what we know and what we don't, between what we can measure and what remains forever beyond measurement. Science is not complete. It never will be. There will always be deeper questions, higher energies to probe, more precise measurements to make, new theories to develop and test. The vacuum stability question stands at the intersection of particle physics, cosmology, and quantum gravity, three of the deepest and most challenging areas of fundamental physics. Progress in any of these fields could dramatically change our understanding of whether the universe is eternal or temporary. That progress is happening now. Experiments are running, theorists are calculating, observations are being made. Each discovery brings us closer to understanding the ultimate fate of everything that exists.
Where does the scientific community stand today? Most physicists agree that based on measurements from the Large Hadron Collider and calculations using the Standard Model, our universe appears to exist in a metastable vacuum state. This is not controversial. It follows directly from established physics. What remains debated is the significance and interpretation of this result. Some researchers, including Joseph Liken, Alessandro Strumia, and others, emphasize that metastability represents a genuine threat to the universe's long-term survival, even if the timescales involved are unimaginably long. Others, including Steven Weinberg and Leonard Susskind, view metastability through the lens of the multiverse, seeing it as evidence for the anthropic principle and the landscape of string theory vacua. Still others maintain that unknown physics, supersymmetry, quantum gravity, or something else will ultimately stabilize the vacuum, making metastability a temporary conclusion based on incomplete knowledge. The consensus is that vacuum decay is real, possible, and mathematically well understood. The disagreement concerns its ultimate meaning and significance. This is how science progresses, not through sudden revelations, but through accumulating evidence, competing interpretations, and gradual convergence toward truth.
We live in an extraordinary time. perhaps the most extraordinary time in human history. For millions of years, our ancestors looked at the sky and wondered. They created myths to explain the stars, stories to make sense of thunder and lightning, religions to answer questions about why we exist. But they couldn't truly investigate. They had no telescopes to peer into deep space, no particle accelerators to probe the fundamental structure of matter, no mathematical framework to describe the quantum realm. We do. For the first time in the 4-billion-year history of life on Earth, conscious beings have developed the tools and understanding to investigate the ultimate fate of the universe itself. We can calculate whether the laws of physics are stable or temporary. We can measure the masses of fundamental particles and use those measurements to predict the behavior of quantum fields at energies far beyond anything we can directly access. We can peer into the quantum structure of space-time itself and ask, will this last forever? And what we found is both humbling and magnificent. Our universe, vast beyond human comprehension, ancient beyond measure, complex beyond imagination, might be temporary. Not in human terms, not even in cosmic terms as we usually understand them, but in the deepest, most fundamental sense, temporary compared to infinity. The vacuum state we inhabit, which allows atoms to form and chemistry to occur and life to exist, may not be eternal. It may be metastable, perched in a local minimum of the Higgs potential, quantum mechanically unstable on timescales of googles of years. This knowledge doesn't diminish us, it elevates us. We are creatures of incredible fortune, existing in a universe that permits our existence. The precise values of the Higgs mass at 125.09 GeV and the top quark mass at 172.76 GeV create a vacuum state compatible with the complex chemistry we're made of. A few % difference in either value and we might not exist, or at least beings like us might not exist. The vacuum state we inhabit is one of perhaps countless possible states the universe could occupy, and we happen to live in one compatible with observers, because only in such states can observers arise to ask questions about their existence. That compatibility might not last forever in the cosmic sense, but it has lasted 13.8 billion years. Long enough for the universe to evolve stars and galaxies, long enough for planets to form, long enough for life to emerge, to evolve, to develop consciousness and curiosity and the capacity for wonder, long enough for us to calculate our own cosmic expiration date. And that is beautiful. The universe might be temporary. Our sun will definitely die. Our galaxy will eventually fade. The laws of physics themselves may one day change. Nothing is permanent, not even physical law. But here, now, in this moment, in this vacuum state, in this universe, we exist. We've walked the surface of the moon. We've sent probes to the edge of the solar system and beyond. We've built machines that can detect gravitational waves, ripples in space-time itself, from black holes colliding billions of light years away. We've measured the mass of fundamental particles to absurd precision. We've developed theories that describe reality from the Planck scale to the scale of galaxy superclusters. We understand, truly understand, that we live in a quantum universe where uncertainty is fundamental, where particles can tunnel through barriers, where fields permeate all of space, where the vacuum itself is not empty, but a seething foam of quantum fluctuations. And we've used this understanding to ask, how long do we have? The answer is uncertain. Maybe forever, if the vacuum is absolutely stable after all. Maybe googles of years, if the metastability calculations are correct. Maybe less, if there's physics we don't understand that changes the answer. But the uncertainty is itself profound. We've reached the limits of what we can know with current physics. We're asking questions at the boundary between the known and unknown, between what can be measured and what remains forever beyond measurement. This is the frontier of human knowledge, and we're standing on it, peering into the abyss, trying to understand the ultimate nature of reality. Vacuum decay reminds us that nothing is guaranteed. The universe is not eternal in any absolute sense. The laws of physics we've painstakingly discovered over centuries may themselves be contingent, temporary, subject to change. But it also reminds us that existence itself is precious. We're here because of an extraordinarily specific and improbable set of circumstances: the right vacuum state, the right fundamental constants, the right history of cosmic evolution. We're a brief flame of consciousness in an otherwise unconscious cosmos. We understand, we question, we wonder. We've built a civilization based on curiosity, on the drive to know why things are the way they are. And we've discovered that the universe we inhabit is stranger, more wonderful, more precarious than our ancestors ever imagined. The bubble at the end of everything might form tomorrow, or in a Google years, or never if we're in a truly stable vacuum after all. We don't know. We can't know with certainty. Quantum mechanics deals in probabilities, and the improbable is never impossible. But we can know this: right now, the universe exists. The laws of physics function. Atoms hold together. Stars burn. Life flourishes on at least one planet, orbiting one star in one galaxy among trillions. And on that planet, conscious beings contemplate their own existence, calculate the stability of the vacuum that sustains them, and marvel at the universe's capacity for complexity, beauty, and meaning. That is enough. The universe is vast. The mysteries are endless. Our existence is improbable. Our time is finite. But we are here. We understand, we wonder, and we continue to ask, why? That question, that fundamental human drive to understand, is perhaps the most remarkable thing the universe has produced. Vacuum decay or heat death or big crunch, eternal or temporary, we exist in this moment. And in this moment, we've achieved something extraordinary. We've understood enough about the fundamental nature of reality to ask meaningful questions about the ultimate fate of everything. The journey continues.